Somewhere beneath the desert sands of Egypt, sealed inside a pit carved directly into the living limestone bedrock, there lies a ship. It has been lying there for 4,500 years, untouched, silent, surrounded by darkness so complete that not a single photon of light has passed through the chamber since the men who placed it there rolled the last enormous limestone slab into position, pressed the seams with white gypsum plaster, and walked away forever. The wood inside that pit, cedar from the mountains of Lebanon, still carries its original color, and the ship, when archaeologists finally measured it in 1954, stretched 43.5 meters from bow to stern, longer than 4 school buses placed end to end, a vessel of such deliberate, engineered elegance that the team who spent 14 years reassembling its 1,224 pieces used words like overwhelming and humbling, not just for the engineering, but for the beauty of the thing itself. Every joint was cut to fractions of a millimeter. Every rope was threaded through channels, carved into the wood with a precision that modern craftsmen have struggled to replicate, even with metal tools. And every single element of this ship, every plank, every beam, every lashing, was built in an age when bronze was a luxury, iron was unknown, and steel was still 3,000 years in the future. This is the story of how human beings, operating with stone, copper, fire, rope, and an extraordinary accumulated understanding of wood, water, and force, built some of the largest ships the ancient world had ever seen. It is a story that stretches from the quarries of the Sinai Desert to the shores of a lost land called Punt, from the cedar forests of Lebanon to the trading ports of the ancient Gulf, from the river fleets of Mesopotamia to the open ocean voyages of the Harappan civilization, along the coasts of what we now call India and Pakistan. It is a story about ingenuity, yes, but also about a kind of confidence in human capability that we have perhaps forgotten, the confidence that says, we do not need what has not yet been invented. We will use what the world has already given us. To understand how deeply strange and impressive this achievement is, you need to spend a moment with the problem itself. Wood and water are natural enemies in the long run. A ship is essentially a controlled argument between the two, and the engineer's job is to make sure the wood wins long enough to be useful. The hull of a large vessel is under constant and varied stress. When a wave lifts the center of a ship, while the bow and stern hang unsupported, the hull tries to bend upward in the middle. This is called hogging. When a wave lifts both ends simultaneously, the middle sags. This is called sagging. Sideways forces push and twist the planking. The weight of cargo, crew, masts, and equipment presses down. The pressure of water pushes up and inward. Every joint in the vessel must absorb and distribute these forces continuously, across years of use, in conditions ranging from calm harbors to open ocean swells. Modern ships handle this with welded steel frames, or with mechanical fasteners, bolts, screws, nails that bite through wood and hold it rigidly against the forces trying to pull it apart. Ancient shipwrights had none of these options, or rather, had versions of them so limited as to be nearly useless for building anything truly large. Copper nails existed, but copper is soft and corrodes badly in salt water. Iron was not yet available in any quantity, and would not be for centuries after the first great ships were built. What the ancient builders had instead was something their modern successors initially did not recognize as engineering at all. They had rope. Not rope as a secondary fastening, not rope as a temporary measure, but rope as a primary structural element, woven through the very bones of the ship, binding planks to beams and frames to hull, in a system so sophisticated that modern naval architects, when they finally modeled it using computer stress analysis, discovered it was genuinely superior to rigid joinery for the conditions these ships actually sailed in. A lashed hull flexes. It absorbs energy rather than resisting it. In heavy seas, a rigidly joined wooden hull will crack at its fastenings because no joint is strong enough to resist all the forces indefinitely. A lashed hull breathes, distributing force through dozens of rope connections simultaneously, each one taking a fraction of the load. It is the difference between a brick wall and a net. One resists until it breaks. The other absorbs and survives. This was not an accident. The builders of the ancient world's great ships understood this principle with a clarity born of thousands of years of watching what happened to boats that were built wrong. They arrived at their solutions through an iterative process we would recognize today as engineering: trial and error, observation, refinement, accumulated knowledge passed from master to apprentice across generations. And they arrived at solutions that were, within their constraints, essentially optimal. But before we can follow this story properly, we need to understand the world those builders were navigating. Not just the waters, but the civilization, the trade networks, the demands that made building such ships necessary in the first place. Because the great ancient ships were not built for pleasure. They were built because someone needed something that existed somewhere else and could not get it by land. They were the children of trade, of hunger, of political ambition, and of a human hunger for connection that seems to be as old as consciousness itself. In the year 2500 BCE, give or take a century or two, depending on how precisely you trust the various ancient calendars that scholars use to reconstruct these timelines, the world was a busier place than most people imagine. Egypt, at this moment, is in the middle of what historians call the Old Kingdom, a period of remarkable political stability and cultural confidence during which the pyramids of Giza were either being built or had recently been completed. The pharaoh who ordered the construction of the Great Pyramid, Khufu, or Cheops as the Greeks later called him, ruled a state of several million people, administered a complex bureaucracy, and commanded an economy capable of feeding, housing, and equipping an enormous labor force year after year. His successors, Khafra and Menkaure, continued this tradition of massive construction, and all three pyramids on the Giza Plateau, along with the Great Sphinx that still stares serenely eastward between them, date to this general period. Egypt at this time was not isolated. It was connected, through a combination of land routes and sea routes, to a network of trading partners that stretched from the eastern Mediterranean to the Red Sea and beyond. To the north and northeast, the Levantine coast, what is now Lebanon, Israel and Syria, provided cedar timber, which Egypt desperately needed and could not produce locally. The Nile Valley grew papyrus, grain and linen in extraordinary abundance, but it grew no suitable shipbuilding timber whatsoever. The trees of Egypt, the sycamore fig, the acacia, produced small, curved pieces of wood, useful for small boats, but utterly inadequate for large ocean-going vessels. If Egypt wanted to build big ships, Egypt had to import the materials to do so, which meant Egypt had to have ships already, which meant the problem was somewhat circular. The Egyptians solved this by building small ships first, trading their way into enough cedar to build larger ones, and scaling upward over centuries until they had a shipbuilding capacity commensurate with their ambitions. To the south, across the Red Sea and down the East African coast, lay the land the Egyptians called Punt, a place of extraordinary mystique in ancient Egyptian records. Punt supplied incense, frankincense and myrrh in quantities that the temple economy of Egypt consumed voraciously, since religious practice required the burning of enormous amounts of aromatic resin. It also supplied ebony, gold, ivory and live animals, including the curious creature the Egyptians depicted in their reliefs as a dog-faced tree climber, almost certainly the baboon. The Egyptians recorded voyages to Punt beginning in the Old Kingdom period, and the trade continued, with gaps, for nearly 2,000 years. Almost all of it was conducted by sea, across the Red Sea and down the East African coast, in ships built for open water. To the east, across the Sinai Peninsula and through the passes of the southern Levant, lay the trading cities of Mesopotamia, the civilization of the Tigris and Euphrates rivers that the Greeks would later call the land between the rivers. Mesopotamia in 2500 BCE was home to some of the world's oldest cities: Ur, Uruk, Nippur, Lagash, and to a commercial culture of remarkable sophistication. The Mesopotamians wrote down their business transactions on clay tablets in a script called cuneiform, and thousands of these tablets survive, giving us a detailed picture of an economy built on grain, wool, oil, and metals. What Mesopotamia lacked, and what it needed desperately, was wood for building and timber for ships, and copper and tin for the bronze that was becoming increasingly central to both construction and warfare. These materials came from the east and north, from the mountain ranges of what is now Iran and Afghanistan, from the Anatolian plateau, and increasingly from a civilization to the southeast, whose extent and sophistication we are still working to understand. That civilization was the Harappan, also called the Indus Valley Civilization, and at its peak, which coincided almost exactly with the period of Egypt's Old Kingdom, it was the largest civilization on Earth by geographic extent, covering an area of roughly 1 million square kilometers across what is now Pakistan, northwestern India, and eastern Afghanistan. The Harappan cities of Mohenjo-Daro and Harappa were, at this period, among the largest urban centers in the world, each housing populations that some estimates put as high as 40 or 50,000 people. They had standardized weights and measures, sophisticated sewage systems, multi-story buildings, and a writing system that remains to this day completely undeciphered. And they had, at the coastal site of Lothal, in what is now the Indian state of Gujarat, what may be the world's oldest purpose-built dock. Lothal's dock, if that is indeed what the large rectangular basin uncovered by archaeologists represents, measures roughly 216 meters long and 37 meters wide. It connects to a tidal river through a sluice gate whose design shows a sophisticated understanding of hydraulics. Ships could enter at high tide. The gate could be closed to maintain water level as the tide retreated, and the ships would float in a controlled environment rather than being left sitting on mud as the tide ebbed. Around the dock, archaeologists found evidence of warehousing, bead-making workshops, and the remains of various trade goods. Harappan seals, small carved stone stamps used to mark ownership of goods, have been found in Mesopotamian archaeological sites, and a few Mesopotamian artifacts have turned up in Harappan contexts, suggesting a trade relationship that involved actual physical exchange across the Arabian Sea. This is the world that needed ships, a network of civilizations separated by water, connected by desire, each with surpluses of some things and desperate shortages of others, and all sophisticated enough to understand that the shortages could be addressed if they could reliably move goods across the distances that separated them. The ships that carried this trade were not luxury items or curiosities. They were infrastructure, as essential to the functioning of these civilizations as roads or canals. And building them, in the absence of metal tools adequate to the task, required solutions that were both deeply practical and genuinely brilliant. The fundamental challenge was not simply one of scale, it was one of material transformation. A tree is a living thing shaped by its own growth, following its own logic of branching and tapering and curving toward the light. A ship plank is a precise geometric object, flat and smooth and cut to exact dimensions, which must fit against adjacent planks, with no gaps large enough to let water through. The transformation from one to the other requires removing enormous amounts of material from the original timber, and doing so with accuracy, measured in millimeters across lengths of 10, 15, 20 meters. With metal saws and planes, this is achievable, if laborious. With stone and copper tools and fire, it requires a completely different set of techniques, a different relationship between the craftsman and the material, and a level of skill that we have systematically underestimated because we have been confused by the modesty of the tools. The Egyptians, the Mesopotamians, the Harappans, and the seafarers of the ancient Mediterranean all discovered, through their own paths of experimentation, that wood could be worked with surprising precision, using a combination of copper adzes, stone abroaders, fire, and an intimate knowledge of how different species of wood respond to each technique. The adze, essentially an axe with its blade set at right angles to the handle, so that it chops across the face of the wood rather than along it, is far more efficient for flattening timber than a saw. And ancient adzes, while made of copper rather than iron, were adequate for the purpose if kept sharp and used by skilled hands. The finishing was done with sandstone and harder stone abroaders, and the result, as the surviving pieces of ancient Egyptian ships demonstrate, could be extraordinarily precise. Fire was used not to destroy the wood, but to shape it. Green timber, freshly cut wood that has not yet dried and hardened, can be bent by heating it with fire or steam until the lignin in the wood softens, bending the plank to the desired curve, and then holding it in that position until it cools and sets. Ancient shipwrights used this technique to produce the curved planks needed for bow and stern sections, and the process left marks on the wood, slight charring on one face, sometimes visible under the natural oxidation of centuries, that archaeologists have been able to identify. The combination of adze working, abrasion, and firebending gave ancient craftsmen control over timber that approached, in practical terms, what was later achievable with metal tools, as long as the craftsmen were willing to invest the necessary time and possessed the necessary skill. And the skill was considerable. We know this not from inference, but from the evidence itself. The Khufu ship, the one buried in that limestone pit at Giza, was built using a technique called shell construction, in which the planks of the hull are assembled first and the internal framework added afterward. Exactly the reverse of the modern method, where frames are built first and planking attached to them. In shell construction, the planks must be precisely shaped and joined so that the hull holds its form purely from the geometry of the planking. The internal framework merely reinforces a shape that the shell itself creates. This requires that each plank be cut and shaped to fit its neighbors exactly, like a three-dimensional puzzle in which every piece is unique, and the whole structure depends on every joint being correct. The craftsman who built the Khufu ship, working with copper tools and stone abraders, achieved this to a standard that modern woodworkers examine with respect. The discovery of the Khufu ship is one of the great archaeological stories of the 20th century, and it begins not with an excavation, but with a smell. In May of 1954, the Egyptian archaeologist Kamal el-Malakh was supervising the clearing of ancient debris from the south side of the Great Pyramid, when one of his workmen noticed something unusual about a long row of enormous limestone blocks set into the bedrock near the pyramid's base. The blocks were sealed with white gypsum mortar, which was not in itself unusual, but what was unusual was the smell rising from a gap in the mortar. It was a sweet, slightly resinous smell, the smell of cedar wood, after 4,500 years in a sealed stone pit. El-Malakh drilled a small exploratory hole through one of the blocks and lowered a mirror to reflect sunlight into the darkness below. What he saw stopped his breath. The pit below was full of wood. Not rotted, not collapsed, not turned to dust or stone by the weight of millennia, but actual, recognizable, intact wood, stacked in careful bundles and tied with rope, filling a chamber roughly 31 meters long, 3.5 meters wide, and 2.5 meters deep. It was immediately clear that what lay below was the disassembled pieces of a very large ship, placed in the pit in a state that would allow it to be reassembled, as if whoever had left it there expected it to be needed again someday. The chamber had been sealed so well, and the desert climate of Giza was so dry, that the wood had barely deteriorated in more than 4 millennia. El-Malakh spent several days contemplating how to proceed before finally deciding to open the pit fully and begin the extraordinary process of documenting, removing, and eventually reassembling what he had found. The documentation alone took years. Each of the 1,224 pieces was photographed, drawn, and catalogued before being removed. The ropes that bound the bundles together were still intact, still pliable enough to untie by hand, which was itself astonishing. The wood was cedar, exactly as El-Malakh's nose had told him, and it had been imported from Lebanon, almost certainly by ship. The irony of using ships to transport wood for ships was not lost on the scholars who studied the find. Some pieces still bore traces of green paint. A few retained evidence of papyrus lashing materials, and scattered among the ship's components were other objects: oars, poles, a wooden canopy that would have shaded the deck, and a set of equipment that gave scholars important clues about how the vessel had been rigged and crewed. The task of reassembly fell to Haj Ahmed Yusuf, an Egyptian restorer who spent 14 years of his professional life working with the ship's components, studying the ancient joints and mortises, and gradually working out how each piece fitted with every other. He described the process in later interviews as like learning a language, in which the grammar was the logic of shipbuilding, and each piece was a word whose meaning became clear only in context. He made mistakes and corrected them. He consulted ancient Egyptian ship paintings and reliefs to understand what the finished vessel should look like. He developed a profound and personal relationship with the material, coming to understand not just how the ship was assembled, but how it was meant to be used. how its designers had thought about the forces acting on a vessel at sea, and how they had engineered the hull to address those forces. The ship that emerged from 14 years of Yusuf's patient work was strikingly elegant. The hull is long and shallow, high at bow and stern in the distinctive papyriform shape that Egyptian ships shared with the papyrus reed boats from which they descended. Both ends curve upward in a graceful arc that recalls the profile of a papyrus bundle when its ends are gathered and tied. This shape was not purely aesthetic. The high, prow deflects waves that would otherwise break directly into the hull, and the high stern provides a stable platform from which a helmsman can see over the deck and use the large steering oar that served ancient ships in place of a rudder. The hull is nearly flat on the bottom, making it suitable for the relatively shallow and calm waters of the Nile and the coastal Red Sea. But the structural strength of the shell construction would have allowed it to handle moderate sea conditions as well. The structural system of the Khufu ship is extraordinarily sophisticated. The planks are joined edge to edge using a technique called mortise and tenon joinery, in which rectangular slots, mortises, are cut into the edges of adjacent planks, and a separate rectangular piece of wood, the tenon, is inserted to span the joint and lock the planks together. This system, used in furniture making since at least the early dynastic period in Egypt, had never before been documented in a vessel of this size. Each tenon in the Khufu ship is precisely fitted, with tolerances that allow the joint to tighten when the wood is wet and swell slightly, creating a naturally self-sealing connection. There are hundreds of these joints in the hull, everyone cut by hand, and they are so consistent in their dimensions and execution that scholars have suggested they may have been cut by a relatively small number of highly specialized craftsmen working to standardize templates. But the mortise and tenon joints, impressive as they are only part of the structural story. The hull is also bound together by a system of rope lashings that pass through V-shaped channels cut in the inner faces of the planks. These channels are invisible from the outside of the hull. The exterior is smooth, but on the interior face of each plank, a channel runs lengthwise, connected at intervals to similar channels in the adjacent planks, creating a continuous pathway for the lashing rope. The rope was threaded through these channels in a pattern that, when complete, created something like a continuous, flexible spine running through the entire hull, holding the planks together against the forces that would otherwise push them apart. When researchers from the American Institute of Nautical Archaeology analyzed this lashing system using modern stress analysis methods, they found that it was genuinely optimal for the conditions the ship would have experienced. The flexibility it allowed, the slight movement of one plank against another, constrained but not eliminated by the lashings, absorbed the cyclic stresses of wave action far more effectively than rigid joinery would have. A rigidly jointed hull accumulates fatigue in its fastenings over time. A lashed hull distributes and dissipates stress continuously, essentially resetting itself between stress cycles. It was, the researchers concluded, a superior solution for wooden vessels operating in the conditions of the ancient Mediterranean and Red Sea, and it had been arrived at not by theoretical analysis, but by millennia of practical experience. The question of whether the Khufu ship ever actually sailed, whether it is a vessel that saw sea service, or a purely ceremonial object built to accompany the pharaoh into the afterlife, is one that scholars have debated since the ship's discovery. The evidence is genuinely ambiguous. Some pieces show evidence of wear and repair that would be consistent with use at sea. The rope, in particular, shows signs of having been under stress, and some of the lashing channels show wear patterns that suggest the ropes were periodically retightened in service, as would be necessary on any lashed hull vessel. On the other hand, the ship's flat-bottomed, shallow draft hull is more suited to calm water than to open ocean, and the lack of a keel, the structural backbone running along the bottom of a ship that provides resistance to the lateral forces of wind and current, would have made it difficult to control in any kind of wind. The most probable interpretation, and the one that most scholars now favor, is that the Khufu ship served as a royal barge on the Nile, used to transport the pharaoh's body from his palace at Memphis to the necropolis at Giza during the funeral ceremonies, and then disassembled and buried adjacent to the pyramid as part of the funerary equipment. But this interpretation does not diminish the ship's significance as evidence of ancient shipbuilding capability. Whether or not this particular vessel sailed the open sea, the techniques used to build it, the shell construction, the mortise and tenon joinery, the lashing system, were the same techniques used to build the ships that did sail to Lebanon for cedar, to the Red Sea coast for the goods of Punt, and along the Nile for the commerce of empire. The Khufu ship is a window into the full range of ancient Egyptian shipbuilding knowledge, preserved in extraordinary completeness, because a pharaoh's servants decided that their king would need a ship in the afterlife, and sealed one for him in the stone of the desert. The second boat pit discovered at Giza, immediately to the west of the first, remained sealed for nearly 4 decades after El Malak's discovery, the subject of considerable academic debate about whether it should be opened and what it might contain. When researchers finally drilled a small exploratory borehole in 1987 and lowered a fiber optic camera into the darkness, they found a second ship in somewhat worse condition than the first due to insect infestation, but still remarkably intact. A Japanese-Egyptian collaborative project to disassemble, conserve, and eventually reassemble this second vessel was ongoing as of the early 21st century, and the work has already revealed details of construction that differ slightly from the first ship, suggesting that the two vessels may have served different ceremonial purposes or may have been built by different workshops operating within the same broad tradition. Together, the two Giza ships represent the most complete surviving evidence of Old Kingdom Egyptian shipbuilding, but they are not the only evidence. The walls of Egyptian tombs throughout the Old and Middle Kingdom periods are covered with paintings and reliefs depicting ships, and the consistency and detail of these representations, showing different types of vessels, their rigging, their crew, the ways they were loaded and steered, makes it clear that these images were made by people who knew ships well and wanted to record them accurately. From these images, and from additional archaeological evidence, including actual ship timbers found at several Old Kingdom sites, we can reconstruct a picture of Egyptian shipbuilding tradition that was already sophisticated in the period of the pyramid builders and became more so in the centuries that followed. To understand where Egyptian shipbuilding wood came from, you need to stand on the edge of what was once a great forest and imagine what it looked like before the millennia of cutting that reduced it to a shadow of itself. The cedar forests of Lebanon, in their ancient extent, covered the mountain ranges that run parallel to the Mediterranean coast of what is now Lebanon, northwestern Syria, and southern Turkey. A green wall of enormous trees rising from the coastal foothills to elevations above 2,000 meters, visible from far out to sea as a dark band against the pale sky of the Levantine summer. Ancient writers describe these forests with something approaching awe. Gilgamesh, the hero of Mesopotamia's greatest epic poem, journeys to a cedar forest so vast and mysterious that it is guarded by a divine monster, and the cutting of those trees is presented as an act of such gravity that it requires heroic justification. Cedrus libani, the cedar of Lebanon, produces timber of exceptional quality by almost any measure. The wood is straight-grained, moderately dense, and highly resistant to both rot and insect damage, properties that made it specifically sought out for shipbuilding in a way that more locally available timbers were not. Ancient Egyptian texts describe it as the choice wood, meru in the Egyptian tongue, and distinguish it from the lesser timbers available domestically. The resin that cedar produces naturally impregnates the wood and inhibits the growth of the marine organisms that attack submerged timber, a property that would have been immediately obvious to anyone who compared the lifespan of cedar-hulled vessels with those built from less resinous woods. Even the smell of cedar, that clean, slightly medicinal aroma that El Malach detected rising from the sealed pit at Giza after 4.5 millennia, is the product of these preservative resins, and ancient peoples were well aware of it. The Egyptian trade for Lebanese cedar appears to have been established no later than the early dynastic period, around 3000 BCE, and may be considerably older. The early trading post and harbour at what is now the Lebanese coastal city of Byblos, called Gubla by the Egyptians and known to them as the port through which cedar reached the Nile, was one of the most important nodes in the ancient Mediterranean trade network for nearly 3,000 years. Egyptian artifacts appear at Byblos in layers dating to the 4th millennium BCE, and Biblian artifacts appear in Egyptian sites from roughly the same period, suggesting a relationship of considerable antiquity. By the time of the Old Kingdom, the relationship between Egypt and Byblos was so close that Byblos has been described by some scholars as an Egyptian protectorate, a place whose rulers understood their prosperity was tied to maintaining Egypt's access to the cedar that Byblos controlled. The voyages to Byblos from Egypt's delta ports would have crossed the open Mediterranean, stretch of water perhaps 300 kilometers, as the crow flies from the Nile Delta to the Lebanese coast. This is not a long distance by modern standards, but in open water terms, with ancient ships and ancient navigation, it was a substantial undertaking. The Mediterranean in this region is characterized by northwesterly winds in summer, which would have made the southward return journey from Lebanon relatively straightforward, but the northward-outward passage considerably more difficult, requiring either beating against the wind or finding a coastal route that offered protection and favorable local breezes. Egyptian ships of the Old Kingdom period were equipped with large square sails, depicted consistently in tomb paintings as rectangular sheets of linen supported by a single horizontal boom at the top and another at the bottom, which were effective for sailing downwind, but much less useful for sailing against the wind. The practical solution was seasonal trading. Sail north to Lebanon in winter or spring, when the northwesterlies are interrupted by periods of southerly winds. Load the timber and sail south with the prevailing winds. Egyptian records of these voyages, carved on the cliff faces of the Wadi Hammamat in the eastern desert, describe expeditions setting out in fleets of several ships and returning laden with cedar logs, other timbers, and luxury goods, including the resin used to make incense. One inscription from the reign of Pharaoh Sneferu, Khufu's father, records the return of 40 ships laden with cedar, which gives some sense of the scale of these operations. 40 ships, each capable of carrying a significant cargo of long timber, would have imported enough wood to supply a substantial shipbuilding program. The logistics of moving long cedar logs across the Mediterranean were themselves non-trivial. Cedar trees suitable for shipbuilding planks could easily reach 30 or 40 meters in length, and a single large plank might require a trunk 6 to 10 meters long and half a meter or more in diameter at the base. Loading such pieces onto a ship, transporting them across open water, and unloading them at the Egyptian end required both physical infrastructure and practical knowledge. Ancient reliefs show logs being towed alongside ships or loaded lengthwise across the deck, and the ports at both the Lebanese and Egyptian ends would have needed the equipment and experience to handle oversized cargo. This was not casual commerce. It was a sophisticated trading operation that required planning, investment, and institutional continuity across multiple generations. The timber trade was not purely Egyptian. Mesopotamian cities were also hungry for cedar, as well as for other timbers not available in the river valleys of the Tigris and Euphrates. The great cities of Sumer and Akkad built their temples and palaces from imported wood, as well as the more locally available fired brick, and the Epic of Gilgamesh, with its central episode of the hero's cedar forest journey, may preserve a memory of actual Mesopotamian timber trading expeditions into the Zagros Mountains or the Amarnus range of southern Turkey, both of which produced useful building timber. The Mesopotamian approach to timber acquisition was somewhat different from the Egyptian. While Egypt relied primarily on sea transport, Mesopotamia used both land routes through the northern mountains and sea routes via the Persian Gulf, and the two approaches were used for different goods depending on the source region and the political conditions at any given time. The Persian Gulf in the 3rd millennium BCE was a highway of commerce, connecting Mesopotamia to the east. Goods from the Harappan civilization, cotton textiles, carnelian beads, lapis lazuli worked into jewelry, timber from the teak forests of the Indian subcontinent, moved westward through the Gulf to the cities of southern Mesopotamia. Mesopotamian grain, wool, and finished goods moved eastward in return. The port of Dilmun, identified with the island of Bahrain, served as the key entrepot for this trade, a neutral ground where merchants from both ends of the route could meet, exchange goods, and be relatively confident of fair dealing. Dilmun appears in Sumerian texts as both a real trading partner and a semi-mythological place of purity and safety, a combination that reflects its genuine importance to Mesopotamian commerce. The ships that carried this Gulf trade were built not from cedar, too expensive and too far away, but from a combination of locally available materials. In Mesopotamia itself, the primary boat-building tradition used reeds rather than wood for small craft. The bitumen-coated reed boat, a technology descended directly from the earliest boat-building experiments in the marshlands of the southern Tigris and Euphrates, could be built quickly, was naturally buoyant, and could be coated with bitumen, the natural tar that seeps from the ground in several places in southern Iraq, to make it effectively waterproof. Reed boats were used for river transport and for coastal work, but they were not suitable for deep-water ocean crossings. And as the Gulf trade grew in scale and ambition, reed boats were supplemented by wooden vessels imported or built from imported timber. The timber for Gulf wooden ships came primarily from teak and other Indian hardwoods, imported from the Harappan coast or from Oman, which had its own tradition of working with timber brought by sea from India. The port of Ras Al Junais in Oman has yielded archaeological evidence of a 3rd millennium BCE shipyard that worked with exactly this combination of materials: Indian timber, Mesopotamian trade goods, and local knowledge of the Gulf's winds and currents. The ships built there would have been substantially different from Egyptian vessels, adapted to the different wind patterns, sea states, and cargo requirements of the Gulf trade, but they shared the fundamental technology of shell construction and rope lashing that characterized almost all ancient wooden shipbuilding. What connected all these traditions was not a single inventor or a single moment of discovery, but a gradually accumulating global conversation about the problems of moving things by water. Each maritime tradition developed its own solutions, adapted to its own materials and conditions, and those solutions were refined over centuries by the accumulated experience of generations of builders and sailors. The result was not a single ancient ship design, but a family of designs, related by their shared fundamental insights: the shell-first construction, the lashed joints, the understanding of wood's response to water and force, but different in their specifics in ways that reflected their different environments. There is a room in the mortuary temple of Hatshepsut, one of Egypt's few female pharaohs, cut into the limestone cliffs at Deir el-Bahri, on the west bank of the Nile, opposite Luxor, where the walls are covered with one of the most extraordinary narrative relief sequences in the ancient world. It depicts, in meticulous detail, the organization, departure, sea voyage, arrival, trading, loading, and return of a royal expedition to the land of Punt, conducted during Hatshepsut's reign in approximately 1470 BCE. The reliefs show the ships, 5 of them, each depicted with the kind of anatomical precision that suggests the artists had stood next to them and looked carefully. And they show the strange wonders of Punt: the houses built on stilts over water, the trees whose roots were dug up and brought back for transplanting in Egypt, the local ruler whose enormous wife required a donkey to carry her, and the piles of goods: incense trees, myrrh resin, ebony logs, gold, ivory, and live animals being loaded aboard the Egyptian vessels. Hatshepsut's Punt expedition is not the first recorded in Egyptian history, but it is the best documented, and it became the template for how Egyptians understood and remembered this remarkable trading relationship. Earlier records from the Old Kingdom period mention Punt as a source of incense and other luxury goods, and the Middle Kingdom produced at least one major expedition. But it is Hatshepsut's reliefs that give us the most complete picture of what these voyages actually involved, and the detail of the ship representations in particular has been enormously valuable to historians of ancient seafaring. The Deir el-Bahri ships are depicted as large, ocean-going vessels with a characteristic design that differs from the Nile riverboats also shown in Egyptian art. They are longer in proportion to their beam, width, than the flat-bottomed Nile barges, and they carry a distinctive piece of equipment that Nile boats do not: a hogging truss. This was a thick rope or cable run over a series of forked stanchions rising from the deck that stretched the length of the ship between bow and stern. When the center section of the hull is in danger of sagging downward between the unsupported ends, the condition called sagging, as distinct from hogging, the hogging truss is tightened by twisting it with a stick, like a tourniquet. and the compression this creates along the length of the hull counteracts the sagging force. It is an elegant, purely mechanical solution to one of the most fundamental problems of wooden ship construction, and the Egyptians had it clearly depicted in their art by at least the Middle Kingdom period, 1,000 years before Hatshepsut. The hogging truss tells us something important about the ships the Egyptians built for open water voyaging. A ship that needs a hogging truss is a ship whose hull, under load, would otherwise be in danger of bending at the center. This means the hull design sacrifices some longitudinal stiffness, the resistance to bending along the length, in favor of other qualities. Most likely the shallow draft and broad beam that made these ships capable of loading and unloading in the shallow, coral-fringed harbors of the Red Sea coast. The hogging truss compensates for the reduced longitudinal stiffness, allowing the hull to remain sufficiently straight under load without requiring the deeper, heavier construction that a more rigid design would demand. It is, in other words, a designed compromise rather than an unintended weakness, and the Egyptians understood exactly what they were doing. The route to Punt from Egypt's Red Sea ports is a matter of some scholarly debate, largely because Punt itself has not been definitively located. The most widely accepted identification places Punt somewhere along the coast of what is now Eritrea, Djibouti, or Somalia, based on the products it supplied. Frankincense and myrrh grow primarily in the Horn of Africa and southern Arabia, and on the general direction and duration implied by the Egyptian texts. Some scholars favor a location in southern Arabia, across the Red Sea from the Horn of Africa. A few have argued for a location in inland Sudan, reached via the Nile and its tributaries. But the consensus, supported by archaeological work at the Red Sea port of Wadi Gawassis, near the modern city of Safaga in Egypt, places the sea route as the dominant means of access, and Punt somewhere in the general region of the Horn of Africa. The Wadi Gawassis site has been excavated by a team of Italian and American archaeologists since 2001, and the findings there have transformed our understanding of Egyptian Red Sea seafaring. The site preserves evidence of a harbor installation used repeatedly over a period of roughly 500 years. From the Middle Kingdom through the early New Kingdom, for the mounting of expeditions to Punt, and to the mines of the Sinai and southern Arabia. Excavations have uncovered large limestone-lined caves that served as storage chambers for ship components, planks, oars, ropes, and the structural elements of the hull frames. And the caves preserve some of the oldest maritime equipment ever found. Ropes of twisted plant fiber, preserved by the extreme desert dryness, still retain their original form and exhibit a laying technique identical to that seen in later Egyptian rope. Wooden planks show the same mortise and tenon joinery and the same V-shaped lashing channels as the Khufu ship, and a collection of inscribed limestone stelae, commemorative inscriptions set up by expedition leaders to record their voyages for posterity, provide detailed accounts of the expeditions themselves. One of the most remarkable finds at Wadi Gawassis was a collection of cedar planks that appear to be the remains of the ships used for these expeditions, stored in the caves when the vessels were disassembled for transport. Overland to the Nile, the Red Sea ports were not, in general, adjacent to the Nile. They were separated from the river by tens of kilometers of desert that had to be crossed on foot and by donkey. Ships could not be taken across this desert intact, but they could be disassembled into their component planks and beams, transported by pack animal, and reassembled at the Red Sea port. The consistency of the joinery systems across the planks found at Wadi Gawasis and those in the Khufu ship suggests that this modular approach to ship construction was intentional. The ships were designed from the outset to be disassembled, transported, and reassembled, which required standardization of components and the ability to rebuild the hull without the original builders being present. This standardization is itself a significant intellectual achievement. Building a ship that can be reliably disassembled and reassembled requires that every joint be designed to tolerance, that the dimensions of structural elements be consistent across the entire vessel, and that some system of marking or sequencing be in place to ensure that pieces are reassembled in the correct order and orientation. The Wadi Gawasis planks show evidence of such marking. Small chisel marks and painted symbols that appear to indicate the position of each piece in the completed hull. And the quality of the joinery is such that the planks could be assembled by workers who had not participated in the original construction, following marks and the logic of the joint system itself. The voyage from a Red Sea port to the Horn of Africa, approximately 2,000 kilometers one way, depending on the exact route and destination, would have taken Egyptian ships several weeks in each direction, following the seasonal wind patterns of the Red Sea and the Northwest Indian Ocean. The Red Sea in summer is dominated by northerly winds in its northern section and southerly winds in its southern section, with a meeting zone in the middle that creates difficult sailing conditions. In winter, the pattern partially reverses, and the winds become more favorable for northward travel in the northern section. Ancient sailors, with centuries of accumulated knowledge of these patterns, would have known when to depart and when to expect favorable conditions, and would have planned their voyages accordingly. The cargo they brought back, incense trees with their root balls intact, as the Hatshepsut reliefs show, represents a level of horticultural ambition that goes beyond ordinary commerce. Transporting live trees across 2,000 kilometers of open ocean, keeping them alive and watered in conditions that would have been challenging even for their own preservation, suggests that the goal was not merely to import incense, but to establish a supply of it permanently within Egypt's borders. The records suggest these trees were planted in the gardens of temples at Thebes and Karnak, though whether any of them successfully established and produced harvestable resin is not recorded. The attempt itself reveals something about the Egyptian relationship to punt. It was not purely transactional. There was a desire to possess the thing itself, to bring punt home in some sense, to make the extraordinary ordinary. This desire, this reach beyond the immediate and available towards something distant and exotic and valuable, is the engine that drove ancient maritime trade. It is a fundamentally human impulse, the same one that has driven exploration and commerce in every era, and it required ships to satisfy it. The Egyptians built the ships because they needed cedar, incense, and gold. They needed cedar for ships, creating a productive circularity that drove the gradual expansion of their shipbuilding capacity over centuries. And in building those ships, using nothing but the tools and materials their world provided, they achieved something that archaeologists and historians are still in: the process of fully appreciating a tradition of wooden shipbuilding that produced vessels of 40 meters and more, capable of ocean voyaging, built entirely without metal fasteners, and refined to a standard of excellence that survived, with modifications, for nearly 3,000 years. If Egypt's maritime achievements are relatively well documented, we have the ships themselves, the port facilities, the inscriptions, the tomb paintings, the seafaring of the Harappan civilization is a subject of tantalizing fragments and suggestive absences. We know that Harappan merchants were present in Mesopotamian cities in the 3rd millennium BCE because their characteristic carved stone seals have been found there. We know that Oman was a trading partner because Harappan-style ceramics appear in Omani sites, and Omani copper appears to have flowed east to the Harappan cities. We know that Lothal had a dock. What we do not have, with any completeness, is the ships themselves. The Harappan writing system, those elegant pictographic symbols that appear on thousands of carved seals and remain completely undeciphered, may contain detailed records of maritime commerce, but until the language is cracked, we cannot read them. The Harappan sites themselves, while extraordinarily rich in material culture, have not yet yielded anything comparable to the Wadi Gawasis cave finds or the Khufu ship pit, a sealed deposit of preserved ship components or ship equipment that would give us a direct window into their shipbuilding technology. What we have instead are representations of ships and boats in Harappan art, painted on pottery, stamped on seals, incised on terracotta tablets, and the structural remains of port facilities, most notably at Lothal, but also at other coastal and riverine sites. The ship representations in Harappan art are few and sometimes ambiguous, but they are consistently interesting. They show vessels with prominent, upswept stems, the structural element at the very front of the hull, and appear to include some form of mast, suggesting that these ships used sail as well as oar. The proportions suggest fairly large, deep-hulled vessels rather than simple coastal dugouts, and the context in which these representations appear, on seals associated with mercantile activity, in port cities near the mouths of rivers opening onto the Arabian Sea, suggests that they are depictions of actual ocean-going trading vessels rather than purely symbolic or mythological images. The challenge of Harappan shipbuilding is one of materials. The great cedar forests that supplied Egypt were not accessible to the Harappan coast, which opened onto the Arabian Sea rather than the Mediterranean. The nearest suitable shipbuilding timber, in quantity, was the teak of India's western coast, a hardwood of exceptional durability and water resistance that would become the standard material for Indian Ocean shipbuilding for the next 3,000 years. Teak grows in the forests of the Western Ghats, the mountain range that runs parallel to India's west coast, and its heartwood is so oil-rich that it is naturally resistant to both rot and the boring organisms that destroy other timbers immersed in seawater. It is also very hard, which makes it more difficult to work than cedar, but also more resistant to damage in service. The construction techniques used for Harappan ships are essentially unknown, because we have no surviving ship components to examine. But the consistency of ancient shipbuilding principles across different traditions and the evidence from later traditions in the same geographic region allows some inference. The sewn plank construction tradition, in which the planks of the hull are stitched together with rope passed through holes bored along their edges, rather than being joined with mortise and tenon joinery, appears to have deep roots in the Indian Ocean region, and it is possible, perhaps likely, that this was the technique used by Harappan shipwrights. Sewn plank vessels were still being built on the Arabian sea coast in historical times, and their builders claimed traditions of great antiquity. The structural principles are the same as those of the Egyptian lashed hull tradition: flexibility through rope connections, distributed force absorption, the use of the rope itself as a primary structural element. But the execution is different. with the rope stitching the edges of planks together rather than running through internal channels. The dock at Lothal, if that is what it is, measures larger than any known contemporary dry dock or wet dock anywhere in the ancient world. The argument that it is indeed a dock rather than some other large rectangular basin depends on several features. The sluice gate at one end, which could be opened and closed to control water level. The presence of mooring rings along the interior walls, and the debris of trade goods found in the vicinity, including carnelian beads, terracotta artifacts, and materials associated with the finishing and loading of cargo. Some scholars have questioned the dock interpretation, arguing that the basin might have served as a reservoir or as part of a water management system for the city. But the balance of evidence seems to support the shipping-related interpretation, and the Lothal dock has been accepted by most researchers as evidence of a sophisticated harbour installation. What happened to the Harappan civilization around 1900 BCE, when it began a decline that eventually led to the abandonment of its great cities, is one of the major unresolved questions of ancient history. The old explanation of an Aryan invasion has been largely abandoned by modern scholars, who see the evidence as more consistent with a combination of factors, including significant climatic deterioration, the drying out of the river systems that supported Harappan agriculture, and possibly epidemic disease. Whatever the cause, the cities were largely abandoned by around 1700 BCE. The trading network collapsed, and the sophisticated maritime commerce that had connected Harappa and Mohenjo-Daro to Mesopotamia and Oman seems to have ceased or significantly diminished for several centuries. But the sailing knowledge did not disappear entirely. The people of the Indian Ocean coasts continued to build boats and sail them, and the traditions they maintained through the dark centuries of Harappan decline eventually fed into the revival of Indian Ocean trade that began in the first millennium BCE. The great sewn plank vessels of the medieval Islamic period, the dhows that sailed from Oman and the Persian Gulf to India and East Africa using the seasonal monsoon winds, were the distant descendants of the Harappan trading tradition, carrying its structural principles: rope-stitched planking, shallow draft hulls, monsoon-dependent seasonal voyaging, across 3,000 years of continuous practice. The monsoon itself, that regular and reliable alternation of wind direction that drives the Indian Ocean circulation, was the key to Indian Ocean seafaring, in a way that the Mediterranean's more variable winds were not. The monsoon blows from the southwest in summer, driving ships eastward from Arabia toward India, and from the northeast in winter, driving them back westward. Any sailor who understood this pattern, and it was surely understood by the people of the Indian Ocean coast long before the period we commonly credit with its discovery, could plan reliable round-trip voyages between Arabia and India, timing the departure and return to coincide with favorable wind directions. The monsoon is, in effect, a scheduling system built into the atmosphere, and the ancient mariners of the Indian Ocean exploited it for millennia before the Greek navigator Hippolus supposedly discovered it in the 1st century BCE, a claim that almost certainly reflects Greek ignorance of existing knowledge, rather than any genuine discovery. The civilization of Mesopotamia produced a different relationship with water than Egypt's, and a different shipbuilding tradition to match. Where the Nile is a single, relatively predictable river flowing north through desert, the Tigris and Euphrates are a pair of rivers that flow broadly south and southeast through a landscape of floodplains, marshes, and shifting channels, prone to unpredictable floods that could destroy entire cities in a single season. The control of water through irrigation canals, levees, drainage channels, and reservoirs was the central engineering challenge of Mesopotamian civilization. And this constant engagement with water produced a practical knowledge of hydraulics that found expression in shipbuilding as well as civil engineering. Mesopotamian boats appear in the earliest layers of the archaeological record, going back to the 5th millennium BCE. The earliest forms were almost certainly made from the bundled reeds that grew in abundance in the southern marshes, the same technique still practiced by the marsh Arabs of southern Iraq in the 20th century, using bundles of giant reeds to construct boats of considerable size. The buoyancy of the reed bundles, combined with a coating of natural bitumen to waterproof the gaps, produced vessels adequate for the shallow, slow-moving waters of the marshland environment. As the civilization expanded and its needs grew more complex, the reed tradition was supplemented and partially replaced by wooden construction, but it never entirely disappeared. The round boat, called the kufa in Arabic, a version of which appears in ancient Mesopotamian art as early as the 3rd millennium BCE, was another indigenous boating tradition. A large, circular or oval basket of woven reeds or withies, coated with bitumen, that could carry substantial loads across calm water, while being so symmetrical that it needed no bow or stern and could be paddled in any direction. Ancient reliefs show kufas loaded with goods, with livestock, and even with stone blocks, being propelled across rivers by boatmen with poles and paddles. The design was so well suited to the Mesopotamian river environment that it remained in use with virtually no change for 5,000 years, surviving into the 20th century in the rivers of Iraq. But for the larger commerce of the Persian Gulf and the occasional open water passage, more capable vessels were required, and Mesopotamia developed a tradition of wooden shipbuilding that drew on imported timber and indigenous rope-making expertise to produce ocean-going craft. The Sumerian epic of Gilgamesh, in the flood narrative that shares so much with the later biblical story of Noah, describes a great vessel built to survive a catastrophic flood. And while the narrative is mythological rather than technical, the dimensions given for the flood vessel are consistent with what we know of ancient wooden shipbuilding practice. A large, roughly cubic vessel with multiple decks, built from timber, bitumen caulked, and loaded with animals, food, and valuables. The more directly historical evidence for Mesopotamian seafaring comes from the cuneiform tablets of the 3rd dynasty of Ur, approximately 2100 BCE, which record in considerable detail the operations of a trading network that reached from Mesopotamia to Oman and probably beyond. These tablets are essentially commercial records, ship charters, cargo manifests, accounts of profits and losses, and they reveal a maritime commerce of surprising sophistication. Ships are leased for specific voyages. Cargo is valued and insured. The risks of sea voyage are accounted for in commercial contracts that bear a remarkable resemblance to modern marine insurance in their basic structure. Merchants pooled capital to fund voyages, sharing both the risk of loss and the profit of success, in arrangements that anticipate the joint stock company by nearly 3,000 years. The tablets name all the ports of call on the Gulf route: Dilmun at Bahrain, Magan at Oman, and Meluha, identified with the Harappan coast, and they describe the goods traded at each stop. From Oman, Mesopotamian merchants bought copper and diorite, a hard black stone used for sculptures and inscriptions. From Meluha, they bought cotton textiles, lapis lazuli, carnelian beads, and timber. In return, They exported grain, wool, oil, and finished goods, including metal implements and finished cloth. The scale of this trade, as recorded in the tablets, was substantial. Individual voyages moved dozens of tons of cargo, and it was maintained over a period of centuries by a merchant class that specialized in Gulf commerce and developed both the institutional knowledge and the personal relationships that made it function. The Gulf traders of ancient Mesopotamia were not naval heroes or explorers in the romantic sense. They were businessmen, motivated by profit, operating within a commercial system that was already old when the earliest of our surviving records were made. What made their voyages possible was not exceptional courage or unusual skill, but rather the accumulated practical knowledge of a maritime tradition that had been developing for centuries before the first tablets were inscribed. They knew the winds, they knew the currents, they knew where the fresh water was and where the anchorages offered shelter. They knew which ports were safe and which were dangerous, which local chiefs were reliable trading partners, and which were prone to seizing cargoes. This knowledge was valuable enough to be kept within families, within guilds, within the networks of established merchants. And its accumulation over generations was what made the Gulf trade possible on the scale that the tablets record. The ships that carried this trade were the result of a different set of compromises than Egyptian ships. The Gulf is a body of water with its own character, relatively shallow, subject to strong seasonal winds, its shores alternating between deep harbors and dangerous shoals. The most suitable vessels for Gulf work were of moderate size, large enough to carry profitable cargo loads, small enough to enter the relatively shallow harbors, and constructed from materials available locally or importable from Oman and the Harappan coast. Teak, as noted, was the premium material, but other hardwoods from the Indian subcontinent also appear in ancient Gulf context. The hard, dense timbers of the monsoon forests of India's west coast were a commodity in their own right, traded westward along the same routes as cotton and copper. Bitumen played a role in Mesopotamian shipbuilding that had no exact parallel in Egypt or the Harappan tradition. The natural bitumen seeps of southern Mesopotamia, the same material used by ancient builders to waterproof walls and floors, and to lay mosaic floors in the temples of Ur, was a readily available caulking material, and Mesopotamian boat builders used it extensively to seal the joints between planks and to coat the exterior of hulls. The characteristic smell of bitumen, that heavy, slightly sweet petroleum odor, must have been a constant presence in the dockyards of ancient Ur and Lagash. As builders heated the solid tar to pour it into gaps and brushed it hot onto hull surfaces, bitumen-coated hulls would have been blacker and heavier than cedar-built Egyptian hulls, and somewhat more resistant to marine-boring organisms, though the bitumen itself required periodic renewal as it cracked and flaked in service. The reed boats of Mesopotamia, coated in bitumen, were also used for river transport in ways that may seem surprising given their simple construction. Some Sumerian tablets describe long river voyages on the Tigris, carrying grain from northern agricultural areas to the cities of the south, and the scale of some of these operations, involving dozens of boats and hundreds of tons of grain, suggests that the reed and bitumen tradition was capable of meeting a substantial fraction of Mesopotamia's internal transport needs. The river itself was the road, and the boat was the cart, and the reed boats were the most cost-effective carts available. only for the open water of the Gulf, where wave action and long periods of immersion would rapidly degrade a reed hull, were wooden vessels necessary. The Mesopotamian shipbuilding tradition eventually fed into the maritime cultures of the Persian Gulf and the Arabian Sea in ways that are difficult to trace precisely, because the documentary record becomes fragmentary after the collapse of the Third Dynasty of Ur around 2000 BCE and remained so for several centuries. But the physical continuity of Gulf seafaring communities, the same coastal villages, the same seasonal fishing and trading patterns, the same accumulated knowledge of wind and weather, ensured that the practical knowledge survived even when the institutional knowledge of the state-organized trading system was temporarily lost. The Gulf traders of the Bronze Age were the ancestors of the Arabian and Indian sailors who would later make the Indian Ocean one of the world's great maritime highways. And the ships they built, without metal fasteners, navigating by knowledge of stars and winds accumulated across centuries, laid the foundation for everything that followed. Perhaps the most persistent misconception about ancient shipbuilding is that it was limited by its tools, that the absence of iron saws, steel planes, and metal drills meant that ancient craftsmen could only produce rough approximations of the precise joinery they needed, and that their ships were correspondingly primitive compared to what would come later. The evidence of the ships themselves refutes this view completely, but the misconception persists because we have an intuitive sense that better tools necessarily produce better results. What we forget is that tool quality and craftsman's skill are not the same thing, and that extraordinary skill can compensate for relatively modest tools to a degree that surprises modern observers. The primary woodworking tool of ancient shipbuilding was the adze, and its use has a long history that makes it much better understood than the popular imagination suggests. An adze consists of a blade mounted perpendicular to the handle, so that when the user swings it in a chopping motion, the blade cuts across the grain of the wood rather than along it. This makes the adze far more efficient than an axe for flattening and shaping wood surfaces, because cutting across the grain removes material in controlled chips, rather than splitting the wood along its grain, which would produce an irregular, unpredictable surface. A skilled adze user can work a rough-sawn plank to a smooth, flat surface with remarkable speed and accuracy, and the marks left by ancient adze work, the shallow, regular chop marks visible on the interior faces of ancient ship planks, show a consistency that can only be the product of long practice. Copper adzes were the primary metal woodworking tools available to Egyptian shipwrights of the Old Kingdom period. And while copper is softer than iron and requires more frequent resharpening, it is entirely adequate for woodworking tasks as long as the cutting edge is properly maintained. Ancient Egyptian workshops maintained grinding stones for this purpose, and the evidence of ancient metal tool hoards shows that adze blades were resharpened repeatedly. The beveled edge is often visible multiple times on surviving copper tool blanks, indicating successive sharpening sessions that moved the edge progressively back along the blade. A copper adze blade might be resharpened a dozen or more times before it was too narrow to be useful, and then it would be remelted and recast. Stone tools, which might seem like a step backward from copper, were actually preferred for some applications because certain stones can be worked to a sharper edge than copper. Obsidian, a natural volcanic glass, can be knapped to edges that are measurably sharper than surgical steel. And obsidian tools were used for fine cutting work well into the Bronze Age in regions where the stone was available. Flint and other high-quality cherts were similarly useful for tasks requiring fine cutting, and ancient craftsmen were highly skilled at selecting the right stone type and knapping technique for different applications. The combination of copper adzes for heavy material removal and flint or obsidian tools for fine cutting gave ancient woodworkers a toolkit that, in practiced hands, was capable of producing work of very high precision. The drill was another essential tool, used to bore the holes through which lashing ropes were threaded and into which tenons were fitted. Ancient drills operated on the bow drill principle, in which a pointed wooden shaft is rotated rapidly by drawing a bow back and forth, its string wrapped around the shaft. The cutting tip of an ancient drill was typically of flint or copper, and these could bore holes in hardwood with surprising speed, far slower than a modern power drill, but not so slow as to be a limiting factor in production. Ancient Egyptian craftsmen have been depicted in tomb paintings using bow drills to bore holes in boat planks, and the holes in surviving ancient ship components are consistent with drill work rather than with chisel cutting. They are round in cross-section and smooth-walled, showing the characteristic circular marks of rotary cutting. Saws presented a greater challenge. Saws for wood require a blade with teeth set at alternating angles so that the kerf, the channel cut by the saw, is slightly wider than the blade itself, preventing the blade from binding in the cut. Copper saws of adequate quality for wood cutting existed in Egypt by the Old Kingdom period, and Egyptian tomb paintings show carpenters using them. But copper saws are inherently limited in how well they hold their set, the tooth angle, because copper is soft and the teeth deform in use, requiring frequent resetting and resharpening. For long, straight cuts through large pieces of timber, ancient craftsmen sometimes preferred to use the adze extensively, taking down material in multiple passes, rather than risk a saw that bound in the cut and wasted the timber. The adoption of iron saws in the first millennium BCE was a significant improvement in woodworking productivity, but it was an improvement in efficiency rather than capability. The ancient craftsmen could produce the same results. They simply took longer to get there. The most underappreciated tool in ancient shipbuilding may have been the template, a shaped piece of wood or other material used to transfer the precise curve or angle of a joint from the master drawing to the actual timber being cut. Ancient shipwrights were working in 3 dimensions on curved surfaces, and maintaining the consistency of joint angles and plank widths across a hull of 30 or 40 meters required some system of reference beyond the craftsman's eye. Templates could be made from thin strips of flexible wood, bent to the required curve, and then used repeatedly to transfer that curve to successive planks. The consistency of joint dimensions in the Khufu ship and other ancient vessels strongly suggests that templates were used systematically, ensuring that each piece was cut to the same standard and that the assembled hull would form the intended shape. Fire, as a woodworking tool, has already been mentioned in connection with bending planks, but it had another use that is less obvious. Wood that is charred on its surface is harder and more resistant to water absorption than untreated wood, and ancient builders in several traditions used controlled surface charring to improve the durability of hull planks, particularly in areas that would be continuously submerged. The charred layer is thin, just a few millimeters, but it creates an effective barrier against the water penetration that causes rot, and against the boring organisms that destroy untreated wood in tropical and subtropical waters. This technique, which involves carefully controlling the fire to achieve charring without deep combustion of the wood, requires skill and knowledge of the behavior of different wood species under heat, and its use in ancient shipbuilding suggests a systematic approach to hull preservation that went well beyond simply trusting the natural durability of the chosen timber. The rope used in ancient ship construction deserves particular attention as a tool material because it was not merely a fastener, but a precisely engineered structural element. The properties of a rope, its strength, its elasticity, its resistance to abrasion and to water absorption, depend critically on the fiber used, the way the fibers are spun into yarn, the way the yarns are twisted into strands, and the way the strands are laid into rope. Ancient rope makers understood these relationships, as evidenced by the variety of rope constructions found in ancient deposits. Different fibers for different applications, different twisting angles for different strength and elasticity requirements, different surface treatments to improve durability in salt water or against the edges of wood. The ropes found at Wadi Gawasis show a level of sophistication in their construction that is consistent with a specialized craft practiced by skilled artisans, rather than an opportunistic use of whatever fiber was at hand. The esparto grass used for ropes in Egyptian shipbuilding, including the rope found in the Khufu ship, produces a fiber of moderate strength but high flexibility and good resistance to rotting when dry. It is not the strongest natural fiber available to ancient rope makers. Hemp, which was available in the Near East by the 3rd millennium BCE, is significantly stronger, and some ancient Egyptian ropes may incorporate hemp fibers. But the esparto ropes of the Khufu ship had survived more than 4,000 years in their sealed pit in a condition that still preserved their original twist and lay, which testifies to the quality of both the material and the construction. Understanding all of this, the tools, the materials, the techniques, the structural principles, is essential for appreciating the full achievement of the ancient shipbuilders. They were not primitive people muddling through with inadequate resources. They were skilled specialists operating within a well-developed technical tradition, using a toolkit that within its constraints was sophisticated and effective, and producing results that were, within those same constraints, essentially optimal. The 40-meter ships they built were not impressive despite their lack of metal fasteners. They were impressive because of how completely their builders understood the material they were working with, and how elegantly they had solved the problems that material presented. By 1500 BCE, the Mediterranean had become a sea of extraordinary complexity, a liquid highway connecting a dozen cultures and half a dozen great civilizations in a web of trade, diplomacy, rivalry, and cultural exchange that would be difficult to overstate in terms of its influence on subsequent history. At the western end of this web sat Egypt, now in its New Kingdom period, administering an empire that reached north into the Levant and south into Nubia. At the eastern end sat the Hittite Empire, centered in what is now Turkey, a formidable military and commercial power with interests in every direction. Between them, occupying the Levantine coast and the Aegean islands and mainland, was a constellation of smaller states: Ugarit, Byblos, Sidon, Tyre on the Levantine coast, Mycenae, Tiryns, Thebes on the Greek mainland, Crete, Rhodes, Cyprus in the Aegean and Eastern Mediterranean, that participated in the trade network as producers, consumers, and intermediaries. The evidence for this network's richness and complexity is spectacular, and in one case, literally spectacular: a shipwreck. In 1982, a Turkish sponge diver named Mehmed Kaka discovered the wreck of a late Bronze Age ship in approximately 44 meters of water off the headland called Uluburun, near the Turkish coastal city of Kos. The wreck has been excavated by teams led by George Boss and Shimal Pulak of the Institute of Nautical Archaeology over a period of 11 seasons, producing one of the most extraordinary assemblages of Bronze Age material culture ever found in a single context. The ship itself, dated by its cargo and its construction details to approximately 1300 BCE, was carrying goods from at least 11 different cultures when it sank, and its cargo list reads like a catalogue of the entire late Bronze Age Mediterranean world. The cargo included 10 tons of copper ingots from Cyprus, cast in the distinctive oxide shape, a rectangular ingot with tabs at the four corners, resembling the shape of a flattened animal hide. That was the standard unit of copper commerce in the late Bronze Age Mediterranean. There were tin ingots, almost certainly from somewhere in Central Asia, since tin sources in the Mediterranean region itself are very scarce. The tin and the copper, mixed in roughly a 10-to-1 ratio, would produce the bronze that was the signature metal of the age. There were glass ingots of several colors, cobalt blue and turquoise, and amber yellow, produced by mixing sand with colorants at high temperature. Glass was rare and precious in this period, traded by weight like metal. There were ebony logs from Africa, a hippopotamus tooth from somewhere on the Nile, an ostrich egg, and a stone scarab bearing the name of the Egyptian queen Nefertiti. There were Canaanite amphoras filled with terebinth resin, used for incense and for sealing wine jars. There were storage jars from Cyprus containing olives, pomegranates, figs, and spices. There were weapons, swords from Mycenae, bronze spearheads, stone mace heads, and tools including adzes, axes, and chisels. There was gold in the form of jewelry and in the form of crude scrap. And there were personal possessions of the crew or passengers, a set of Mycenaean-style balance weights and a set of Egyptian-style balance weights, suggesting that the ship was prepared to operate in both commercial systems. A stone cylinder seal of Mesopotamian type, Canaanite jewelry, ivory gaming pieces, and a gold medallion in the form of a woman who may be a goddess. The Uluburun ship itself, reconstructed from its surviving hull remains, was approximately 15 meters long, smaller than the great ships of the Punt expeditions, but substantial by ancient standards, and clearly capable of ocean voyaging, given the evidence of its final voyage. The hull planking was cedar, jointed with tenons in the Egyptian manner, though with some differences in detail that suggest the ship may have been built in a Levantine or Cypriot yard rather than in Egypt. The evidence of its cargo and the diversity of weights and commercial systems represented among the crew's equipment suggests that this was a genuinely international vessel, owned or chartered by merchants operating simultaneously in multiple trading systems, carrying goods for multiple customers, and prepared to do business by the rules of whatever culture they encountered at each port. The Uluburun ship represents the most spectacular single find from the late Bronze Age maritime network, but it is far from the only one. The Cape Gelidonia wreck, also off the Turkish coast, and also excavated by George Boss in a pioneering project in the 1960s that was among the first systematic underwater excavations in history, produced another late Bronze Age cargo of copper and tin ingots, along with a suite of merchants' tools and equipment. Other wrecks from the same period have been found in the Aegean and the Eastern Mediterranean, and together They build up a picture of a trade network of considerable density and sophistication, served by ships that crossed open water regularly and carried mixed cargoes that had often changed hands multiple times before reaching their final destination. The ships of the late Bronze Age Mediterranean were built in a tradition that had evolved significantly from the Old Kingdom Egyptian shell construction, though without abandoning its fundamental principles. The mortise and tenon joinery, documented in the Khufu ship, appears in virtually every Bronze Age wreck investigated, suggesting that this technique spread from Egypt to become the standard joinery method across the entire eastern Mediterranean. But the details of construction varied. The thickness of the tenons, the spacing of the mortises, the use of pegs to lock the tenons in place. A technique absent from the Khufu ship, but present in many later wrecks, all differ between different building traditions, providing archaeologists with a way of distinguishing ships built in different regional yards. The late Bronze Age ships, unlike the Old Kingdom Egyptian vessels, appear to have been built with internal keels, structural members running along the center of the hull bottom that provided longitudinal stiffness and improved seakeeping in the choppier waters of the Aegean compared to the relatively calm Red Sea. The development of the keel is one of the most significant advances in ancient shipbuilding history, because a keeled hull can work to windward, sail at an angle to the wind, to a degree that a flat-bottomed keelless hull cannot. This expanded the range of conditions in which ships could reliably operate and reduce their dependence on favorable winds, making year-round trading more feasible and allowing access to harbors that would have been unreachable against the wind in keyless vessels. The late Bronze Age network came to an abrupt end around 1200 BCE in a series of disruptions so severe and so rapid that they constitute one of the great historical puzzles of the ancient world. Within a period of roughly 50 years, the Hittite Empire collapsed. The Mycenaean palace culture on mainland Greece collapsed. Ugarit was destroyed and never rebuilt, and Egypt was severely disrupted by a series of invasions by a confederacy of peoples the Egyptians called the Sea Peoples, whose origin and identity has been debated by scholars for 2 centuries without reaching a definitive conclusion. Some of the most detailed Egyptian records of the Sea Peoples come from the reign of Rameses III, who fought them off in a great battle circa 1176 BCE, depicted on the walls of his mortuary temple at Medinet Habu. The Medinet Habu reliefs show the naval battle between Egyptian and Sea People ships with remarkable detail, and they are among the most important sources for late Bronze Age naval technology. The Sea People ships depicted have curved prows and sterns decorated with bird heads, a distinctive feature that allows them to be identified in contexts as far apart as the Aegean and the Levantine coast. The Egyptian ships in the same reliefs show the latest development of the Egyptian maritime tradition, still using the high papyriform bow and stern, still equipped with a hogging truss, but now larger, higher-sided, and apparently equipped with a fighting platform at the bow. The battle is depicted as a chaotic melee in which Egyptian archers fire into crowded enemy vessels from the shore and from other ships, and the Sea People ships are shown capsizing or being captured, their rigging tangled and their crew falling into the sea. Whether the Sea Peoples were migrants driven by the same systemic crisis that destroyed Mycenae and the Hittites, or raiders from a different background entirely, their appearance marks the end of the Bronze Age Mediterranean network and the beginning of a centuries-long period of reduced complexity and simpler trade. The palace economies that had organized and sustained the network collapsed, and with them the administrative capacity to fund large-scale timber procurement, ship construction, and organized long-distance trading expeditions. The Iron Age that followed would eventually produce even larger ships and more extensive trade networks. But the transition was not seamless. There was a genuine Dark Age, a period of reduced population and simpler material culture in many parts of the Mediterranean, before the recovery began. What survived this collapse, and what made the recovery possible, was the practical knowledge embedded in the communities of craftsmen and sailors who kept building and sailing small boats, even when the great empires that had funded large-scale shipbuilding were gone. Tradition in human societies is not merely cultural conservatism. It is the storage medium for practical knowledge that has been validated by experience over long periods. The mortise and tenon joinery that had built the Khufu ship was still being used in the boats built on the Mediterranean coast in the centuries following the Bronze Age collapse, not because anyone had decided to preserve it as a historical artifact, but because it worked, and the craftsmen who used it knew it worked, and they taught it to their apprentices because it was the right way to do the job. Out of the wreckage of the Bronze Age Mediterranean, one culture emerged into the early Iron Age, with its maritime tradition not only intact, but actively expanding. The Phoenicians, inhabiting the Lebanese coast from Tyre and Sidon in the south to Byblos in the north and beyond, had been participants in the late Bronze Age network as suppliers of cedar and intermediaries in the Levantine trade. When the network collapsed, they were among its few survivors, and they turned their inheritance of maritime knowledge, their remaining stocks of cedar, and their commercial connections into one of the most remarkable maritime expansions in ancient history. The Phoenicians are often credited with a series of maritime firsts that range from the plausible to the debatable, but their general reputation as the great sailors of the ancient world is well earned. By approximately 1000 BCE, as the Bronze Age Dark Age was beginning to lift, Phoenician merchants were already re-establishing trading connections across the eastern Mediterranean. By 900 BCE, they had reached the western Mediterranean, establishing trading posts and eventually colonies along the coasts of what are now Tunisia, Sicily, Sardinia, and Spain. By 800 BCE, the city of Carthage, a Phoenician colony on the North African coast, near what is now Tunis, had been founded and was beginning its own expansion into the western Mediterranean trade. The ships that carried Phoenician commerce were built from the same cedar forests that had supplied Egypt for 2,000 years, and they used the same fundamental construction techniques, mortise and tenon joinery. Shell-first construction that had been developed in the Old Kingdom period, but the Phoenicians made significant advances in ship design that reflect both the different conditions of Mediterranean seafaring in the Iron Age and the different commercial priorities of a maritime trading culture, operating without the state-organized resource procurement of the great Bronze Age empires. Phoenician merchant ships were deep-hulled and round-bodied, compared to the shallow draft Egyptian vessels of the New Kingdom, built for carrying maximum cargo in minimum space, rather than for shallow water access. They were the container ships of the ancient world, optimized for the movement of goods over the open sea, rather than in and out of shallow rivers. The surviving evidence for Phoenician ships comes from several sources. Assyrian palace reliefs of the 8th and 7th centuries BCE show Phoenician ships in considerable detail, as the Assyrian kings hired Phoenician fleets to support their campaigns and depicted them in their monumental art. These reliefs show ships with a distinctive rounded hull profile, deep and broad amidships, narrowing at both ends, and a prominent ram at the bow, a weapon feature that will become increasingly important in the warships of the classical period. The merchant vessels lack the ram but share the basic hull form, and some reliefs show them loaded with timber. Cedar logs for the Assyrian building programs, transported by the people who had been cutting and selling cedar since the days of the Old Kingdom pharaohs. The Phoenicians also built the vessels that their competitors and successors in the Greek world would eventually call the birames and triremes, the oared warships of the classical Mediterranean. The development of the dedicated warship from the merchant vessel is a process that can be traced through the Bronze Age reliefs to the Iron Age Phoenician and Greek depictions, and it represents a significant evolution in the demand placed on shipbuilders. A warship does not need to carry large amounts of cargo. It needs to move fast, sustain high speeds under oar for extended periods, and survive the impact of ramming and being rammed. These requirements call for a different hull design, lighter, narrower, with a long, clean underwater hull, and a different structural approach than the round-bodied merchant ship. The answer the Phoenicians and Greeks developed was the outrigger and the multi-bank oar system. By extending the width of the rowing deck beyond the hull, with a projecting outrigger, and stacking oarsmen on multiple levels so that more of them could be fitted into the length of the ship without making it so wide as to be unmaneuverable, ancient naval architects achieved a power-to-weight ratio in their warships that has rarely been exceeded in human-powered vessels. The trireme, the standard warship of the classical Greek period, carried approximately 170 oarsmen arranged on 3 levels, each pulling an oar of carefully calculated length to ensure that all 3 levels of oars could be worked simultaneously without interference. The engineering that made this possible, the geometry of the 3-level oar arrangement, the structural design of the outriggers, the optimization of hull shape for minimum drag at ramming speed, was developed without iron tools or metal fasteners, using cedar planks joined with mortise and tenons, and lashed with rope in the tradition that had begun, as far as we know, with the builders of the Khufu ship. The trireme construction has been the subject of one of the most ambitious experimental archaeology projects in history, the building and sailing of a full-scale reconstruction, the Olympias, by a team of British scholars and Greek craftsmen in the 1980s and 1990s. The Olympias was built using ancient construction methods as closely as modern materials regulations and practical constraints allowed. Wooden hull, mortise and tenon joinery, although with modern metal fastenings, as well given the safety requirements of a vessel carrying a crew of modern volunteers. Trials of the Olympias demonstrated that the ancient design was highly effective. The reconstructed trireme reached speeds of over 9 knots under oar, enough to generate significant impact force in a ramming attack, and was maneuverable enough to execute the tactical turns described in ancient naval battle accounts. The project also revealed unexpected details of ancient construction, including the extreme lightness of the trireme hull, necessary for the speed requirement, and the consequent fragility of the vessel, which was designed to be hauled ashore each night rather than moored in the water, because prolonged immersion would have waterlogged the light planking and significantly degraded performance. The transition from the Phoenician-dominated Mediterranean of the early Iron Age to the Greek-dominated Mediterranean of the classical period involved not a replacement of maritime technology, but a borrowing and refinement of it. The Greeks, or rather, the extraordinarily diverse collection of city-states and regional cultures that we group under the name Greek for convenience, were not naturally a maritime people in the earliest period of their history. The Mycenaean palace culture of the Bronze Age had been maritime, but the Dark Age following the Bronze Age collapse had reduced Greek seafaring to a shadow of its earlier extent. The recovery, when it came in the 8th century BCE, was powered in part by contact with the Phoenicians, from whom the Greeks learned not only the alphabet that would transform Greek literacy, but also the advanced shipbuilding techniques that would eventually give them command of the Mediterranean. The Greek merchant class that grew wealthy on the revived Mediterranean trade of the 8th and 7th centuries BCE used ships that were essentially Phoenician in their construction, and the gradual evolution of distinctly Greek ship designs from this starting point is visible in the art. The painted pottery that survives in enormous quantities from Greek sites and that depicts ships with remarkable frequency and, in the best examples, considerable accuracy. From the geometric period of the 8th century, with its highly stylized but recognizable ship images, to the red figure vase painting of the 5th century, with its detailed, almost technical representations of rigging and hull construction, the Greek artistic tradition provides a running visual commentary on the development of Greek shipbuilding over 5 centuries. The classical Greek merchant ship, the round ship, as it was called in contrast to the long, narrow warships, was a medium-sized, deep-hulled, predominantly sailing vessel of roughly 15 to 30 meters in length, carrying a crew of perhaps 15 to 30 men and a cargo measured in tens of tons. It was not radically different from Phoenician merchant ships of similar size, using the same basic construction technology, but it was refined and adapted for the specific conditions and commercial requirements of the Aegean and Eastern Mediterranean. Several wrecks of classical Greek merchant ships have been found in Mediterranean waters, and they show hull constructions that are recognizably descended from the Bronze Age tradition. Mortise and tenon joinery, cedar planking, internal frames fitted after the shell was assembled. One of the most completely excavated of these wrecks is the Kyrenia ship, found in 1965 in approximately 30 meters of water off the northern coast of Cyprus near the town of Kyrenia, and excavated by Michael Katzeff and a team from the University of Pennsylvania. The Kyrenia ship dates to approximately 300 BCE, late in the classical period, and survives in unusually good condition, with much of its hull planking intact and substantial remains of its cargo and equipment. The ship is about 14 meters long and 4 meters wide, smaller than some ancient merchant vessels, but typical in its proportions and construction. The mortise and tenon joinery is clearly visible in the surviving planking, and the tenons are locked in place with small wooden pegs driven through the plank face into the tenon, a technique also seen in the Uluburun ship that prevents the tenons from working loose as the hull flexes in service. The cargo of the Kyrenia ship, approximately 400 wine amphoras from various islands, 29 millstones of basalt from a quarry on the island of Nisyros, and a small quantity of almonds, gives a picture of the normal commerce of a small merchant vessel of the period. Mundane goods, not luxury items, moved in bulk between the agricultural islands and the consuming cities of the mainland, the kind of unglamorous but essential trade that was the actual backbone of the ancient economy, as distinct from the dramatic long-distance expeditions to Punt and Lebanon that receive more attention in the ancient records and in modern popular accounts. Most ancient ships were Kyrenia ships, not Punt expedition fleets. The Romans inherited the Greek maritime tradition, as they had inherited much of Greek culture, adopted and adapted it for their own needs. Roman naval shipbuilding represented the most organized and systematic application of ancient wooden shipbuilding technology that the ancient world produced. Rome's naval construction programs during the Punic Wars, with Carthage in the 3rd and 2nd centuries BCE, are recorded as involving the building of hundreds of warships in periods of just a few months, implying a shipbuilding industrial capacity of astonishing scale. The Polybius account of Rome building a fleet of 120 warships in 60 days, an often cited figure, may be an exaggeration, but even if the actual number and time were doubled, the achievement would represent an extraordinary mobilization of skilled labor, organized timber supply, and manufacturing capacity. Roman merchant ships grew significantly larger than their Greek predecessors, driven by the Roman need to supply the city of Rome, a metropolis of 1 million people by the 1st century BCE, with grain from Egypt and North Africa. The grain ships that crossed the Mediterranean from Alexandria to Rome were the supertankers of the ancient world, enormous, round-hulled vessels of perhaps 50 meters in length and carrying hundreds of tons of grain, dependent on the ability to fill their holds completely to be economically viable, because the thin profit margin grain trade required maximum cargo capacity to generate adequate returns. These ships were built with iron nails alongside the traditional wooden tenons, reflecting the increasing availability of iron in the Roman period. But the fundamental structure, cedar and pine planking, shell-first construction, mortise and tenon joinery, remained continuous with the tradition going back to the Old Kingdom of Egypt. The wreck of a large Roman grain ship, excavated at Madrague de Gien on the southern French coast in the 1970s and 1980s, gives a sense of the scale these vessels achieved. The Madrague de Gien ship, dated to approximately 60 BCE, was approximately 40 meters long, comparable to the Khufu ship, and carried an estimated 6,000 to 7,000 amphoras of wine, each holding about 26 liters. The total cargo was approximately 400 tons of wine, more than any pre-modern wooden ship we have direct evidence for carrying. The hull construction combined mortise and tenon joinery in the outer planking with iron spike fastening in some of the inner structural members, a hybrid approach that reflects the transitional period of Roman shipbuilding in which the exclusively wooden fastening tradition was beginning to give way to the Iron Age of maritime construction that would characterize medieval and early modern ships. The survival of the pre-metal fastening tradition into the Roman period, and as we shall see, well beyond it, is not merely conservatism or inertia. Shipbuilders are conservative because their mistakes are expensive and sometimes fatal, and they abandon proven techniques only when they are convinced that the alternative is demonstrably better. The gradual adoption of iron in Roman shipbuilding was driven by the increasing availability and decreasing cost of iron in the Roman economy, not by any fundamental inadequacy of the wooden fastening system. Where iron was expensive or unavailable, as in the Indian Ocean and the Red Sea, the mortise and tenon, or sewn plank traditions, continued without interruption into and beyond the medieval period. While the Mediterranean tradition of wooden shipbuilding was evolving through its Phoenician, Greek, and Roman phases, the Indian Ocean had its own shipbuilding tradition that had been developing in parallel, and that, in some respects, was even more conservative and long-lived. The sewn plank boats of the Arabian Sea and the Persian Gulf, vessels whose planking was stitched together with coconut fiber rope, rather than fastened with wooden tenons or metal nails, represented a technology so well adapted to its environment that it survived with only incremental modifications for at least 3,000 years, and perhaps considerably longer. The technique of sewing planks together with rope, rather than joining them with tenons or nails, produces a hull that is structurally different from either the Egyptian Mediterranean or the modern nail-fastened traditions, but different in a way that has specific advantages in the Indian Ocean context. A sewn hull is, even more than a tenon-jointed and lashed hull, completely flexible. The individual stitches can tighten or loosen slightly in response to the forces acting on the hull, and the entire structure behaves like a basket rather than like a rigid box. In the conditions of the Indian Ocean, deep ocean swells that lift and twist a ship, rather than the relatively shallow, steep seas of the enclosed Mediterranean, this flexibility provides a cushioning effect that reduces the peak stresses on the planking and joinery. Sailors in sewn boats reported that the hull moved visibly in heavy seas, like a living thing, and found this reassuring rather than alarming. It was the silent hull that worried them, because it might mean the fastenings had become rigid and could break. The fibers used for sewing in the Indian Ocean tradition were primarily coconut coir, the fibrous husk material of the coconut palm, which has the useful property of swelling when wet, causing the stitches to tighten rather than loosen when the hull is immersed. This self-tightening property is so valuable that coir was preferred for hull sewing even in regions where stronger plant fibers were available, because the strength advantage of stronger fibers was more than offset by the disadvantage of their not swelling in water. Ancient seafarers discovered this through experience, and the preference for coir in Indian Ocean sewn boat construction is consistent across millennia of the tradition. The timber used in Indian Ocean sewn boats was predominantly teak, though other Indian hardwoods, including kokam, Indian laurel, and calamander, were also used depending on the region and the application. Teak's combination of oil content, hardness, and workability made it nearly ideal for a tradition that depended on drilling thousands of small holes through the plank edges for the sewing needles, a process that in a softer or more oil-poor wood would result in rapid deterioration around the holes and eventual failure of the stitching. In teak, the holes seal themselves to some degree with the natural oil of the wood. The coir expands to fill the remaining gaps, and the junction between rope and wood is remarkably durable in service. The planks in a sewn boat are not only sewn at their edges, they are also attached to internal frames with sewing, and the frames themselves are often composite structures of short pieces of wood bound together with rope to achieve the required curve. This composite approach, using rope to assemble multiple small pieces of wood into a single structural member, allows the builder to work with relatively short timbers while achieving the structural complexity of a large vessel. And it was particularly well suited to the Indian Ocean trade context, where the best timber came from the teak forests of India, but had to be transported to the building sites of Arabia and East Africa as relatively small pieces that could be loaded on the same trading ships that carried other goods. The Arab geographer and traveller Al-Masudi, writing in the 10th century CE, described the sewn boats of the Indian Ocean with a combination of admiration and some perplexity, noting that they carried no nails and that their planks were sewn with fibre cord, and remarking that this made them resilient in the conditions of the Indian Ocean, while making it impossible to carry them into the Mediterranean, where the rougher seas and different wave patterns caused them to fall apart. Whether his observation about Mediterranean incompatibility is accurate or merely reflects the different expectations of Mediterranean sailors, encountering an unfamiliar hull type is unclear, but it suggests that the differences between the two traditions were well understood by sophisticated observers of the 10th century, even if the underlying structural reasons for those differences were not articulated in modern engineering terms. The most dramatic demonstration of the viability of ancient sewn-boat construction in the modern era came in 1980 and 1981, when the explorer and adventurer Tim Severin built a replica of a 9th century Arab sewn-boat, a vessel he named the Sohar, after the Omani port city associated with the Sinbad the Sailor stories, and sailed it from Oman to China, roughly 8,000 kilometers, following the ancient trade route described in medieval Arab texts. The Sohar was built by traditional Omani craftsmen using traditional techniques, stitched with coconut fiber rope, caulked with fish oil paste, and built from timber imported from India. The voyage took 7.5 months, including a stop in Sri Lanka and a terrifying passage through a typhoon south of China, and it arrived successfully in Guangzhou, the old Canton, proving beyond reasonable doubt that the ancient technology was capable of the ocean voyages attributed to it. Severin's Sohar was approximately 20 meters long and displaced approximately 60 tons, somewhat smaller than the largest ancient vessels of the Indian Ocean tradition, which contemporary accounts suggest reached lengths of 40 to 50 meters and could carry several hundred passengers and crew. The great ocean-going dhows, described by Arab geographers of the medieval period, were monsters by the standards of the ancient Mediterranean, built for the long passages of the Indian Ocean under the monsoon winds, and capable of sustained voyaging that would have been beyond the reach of most Mediterranean ships of the same period. The largest of them, called the bagla, a word meaning mule, suggesting a beast of burden rather than a racer, could carry several hundred tons of cargo and required a crew of 50 or more men to handle the vast spread of lateen sail needed to drive such a hull. These great vessels were the culmination of a shipbuilding tradition that had been developing without metal fasteners and without interruption since at least the period of the Harappan civilization, and possibly earlier. They were not primitive survivals of a superseded technology, but sophisticated and well-adapted vessels, refined over centuries to the point where they were essentially optimal for the conditions of the Indian Ocean trade. And they were still being built by traditional methods: sewn planking, coir lashing, teak timber, fish oil caulking, as recently as the 20th century in the coastal communities of Oman, India, and East Africa, keeping alive a thread of practical knowledge that stretched back farther than most of the cultural institutions we consider ancient. To build a ship capable of ocean voyaging is one achievement. To find your way across open water without charts, without compasses, without GPS, this is another achievement entirely, and it is one that the ancient world accomplished with a combination of astronomical knowledge, systematic environmental observation, and accumulated experience that represents one of the most extraordinary intellectual achievements of pre-scientific humanity. The fundamental challenge of ocean navigation is determining your position relative to your destination when there are no landmarks in any direction, only water and sky. A navigator on a featureless ocean needs to answer two questions. Where am I now? And in which direction is where I want to be? In the modern era, these questions are answered by GPS, which determines position by measuring the time delay of signals from multiple known satellites. In the era of magnetic compasses, roughly the last 1,000 years in the Western tradition, the second question was answered by the compass, and the first by a combination of compass and celestial observation. In the period before the compass, both questions had to be answered from the sky itself. The sky as a navigation system is extraordinarily rich in information for those who know how to read it, and the ancient mariners knew how to read it with a thoroughness that most modern people would find surprising. The most basic celestial navigation fact, that the sun rises in the east and sets in the west, provides directional information. During the day, when the sun is visible, the height of the sun at noon above the horizon is a function of latitude, and a navigator who knows what noon altitude corresponds to a given latitude can maintain that latitude by keeping the noon sun at the right height. This technique, called latitude sailing, requires no instruments beyond a way to measure the angle of the sun above the horizon, which can be done with remarkable accuracy using a simple gnomon, a vertical stick, or even by using a finger width as a rough angle measure. At night, the stars provide both directional and positional information. The most obvious example is Polaris, the North Star, which sits within about 1 degree of the true north celestial pole, and whose altitude above the northern horizon is equal to the navigator's latitude. A navigator heading northward from Egypt toward Lebanon could maintain their course by keeping Polaris at the right height. Returning southward, they would steer with Polaris behind them and use a southern sky star or constellation to maintain their heading. The Egyptians were keenly aware of the stars and had a systematic knowledge of which stars rose and set at which times of year. The heliacal rising of Sirius, the dog star, was used to predict the annual Nile flood and appears in the oldest Egyptian astronomical records. Extending this knowledge to navigation was a natural step for a culture that already had a sophisticated understanding of celestial cycles. But the stars and sun were only part of the ancient navigator's toolkit. The ocean itself provides information to those trained to read it. The direction and character of ocean swells, long waves generated by distant storms that maintain their direction for thousands of kilometers, can indicate the direction of ocean features even when the sky is overcast. The color and temperature of the water changes near shores and currents. The types of marine life visible at the surface vary systematically with latitude and proximity to land. The direction of wind and the character of clouds are influenced by nearby land masses. Seabirds fly away from land to feed in the morning and return at evening, providing a directional cue that could indicate the presence of land at distances of several hundred kilometers. The Polynesian navigators of the Pacific are the most thoroughly studied practitioners of this kind of wayfinding, and what was learned from them in the 20th century has transformed our understanding of what ancient mariners were capable of. The Polynesian tradition of non-instrument navigation, still practiced by a small number of traditional navigators as recently as the late 20th century, uses all of the environmental cues described above and more. The texture of swells reflected from islands, the persistent wind shadows of high islands that alter wave patterns for many kilometers around them, the slight luminescent glow visible above inhabited islands at night from the reflection of fires on the clouds. Polynesian navigators trained from childhood in these techniques could consistently navigate between islands, separated by hundreds or thousands of kilometers of open ocean, with accuracy that impressed and initially bewildered Western observers who expected accuracy to require instruments. The relevance to ancient Mediterranean and Indian Ocean navigation is direct. The Polynesian tradition developed independently of the Near Eastern maritime traditions, but the environment it operated in was in many ways more challenging. Pacific islands are smaller and more widely separated than Mediterranean coastlines or the Red Sea shores, and the fact that it produced such accurate results without instruments is powerful evidence that non-instrument navigation across ocean passages is entirely feasible for trained and experienced practitioners. What the ancient Egyptian or Phoenician or Harappan navigator knew about the stars, swells, winds and wildlife of their particular ocean was specific to that ocean and might not be transferable to the Pacific. But the cognitive approach, systematic observation, accumulated knowledge, pattern recognition, confident inference, was the same. For the Red Sea route to Punt, ancient Egyptian navigators would have needed a detailed knowledge of the Red Sea's seasonal wind patterns, its numerous reefs and shoals, the position and character of the reliable watering points along its shores, and the conditions of the passage through the Bab el-Mandeb Strait at its southern end. These are relatively straightforward challenges for a navigation tradition that had been operating in the Red Sea for centuries, and the ancient texts suggest that the Punt expeditions were conducted with considerable confidence. They departed at known times, followed known routes, and returned with reliable predictability. The sense of adventure that we project onto these voyages may be more a product of our own ignorance of ancient conditions than of the actual feelings of the Egyptian sailors who made them. For the Indian Ocean monsoon routes, the knowledge required was more complex, but equally systematic. The monsoon reversal is a large-scale, reliable phenomenon, but its detailed behavior, the timing of onset and withdrawal at different latitudes, the distribution of storms within the monsoon season, the character of the inter-monsoon periods, varies in ways that experienced sailors would have known and used. The Arab sailors of the medieval period, who navigated the same routes, left written records of their navigational knowledge that describe in detail the star paths, wind patterns, and sea signs used for different passages. And this knowledge was the product of centuries of accumulated observation that ultimately had its roots in the pre-Islamic trading tradition. The most sophisticated ancient navigational tool that we have direct evidence for is not a physical instrument at all, but a conceptual one. The concept of the star path, a sequence of stars that rises or transits in a consistent compass direction relative to the navigator's destination, providing a series of reference bearings that can be used to maintain course through the night. Hawaiian navigators used star paths of extraordinary complexity, memorizing the rising and setting points of hundreds of stars for navigation to dozens of different destinations. The evidence suggests that ancient navigators in the Mediterranean and Indian Ocean use similar conceptual frameworks, and that the accumulated star knowledge represented in early astronomical texts, which are often dismissed as purely religious or agricultural documents, may in fact encode navigation knowledge of practical value. The confidence with which ancient ships made long ocean passages, the routine crossings of the Red Sea to Punt, the Phoenician voyages to Spain and beyond, the Arab dhows running before the monsoon to India, reflects a navigational competence that was real, not legendary, and that was the product of systematic training and accumulated knowledge passed across generations. The ships were built to make these voyages. The navigation knowledge was developed to guide them, and the two together produced a maritime capability that served the trade needs of the ancient world with a reliability that may surprise us when we stop, projecting our own ignorance onto the past. The distinction between military and merchant ships in the ancient world was never as clear as it might seem from a modern perspective, because the same builders, the same harbours, and often the same crews served both purposes. But the development of dedicated military vessels, ships designed specifically for fighting rather than for trading, represents an important evolution in ancient shipbuilding demands, because military ships impose requirements quite different from those of merchant vessels, and meeting those requirements drove innovations in hull design and construction that eventually fed back into the commercial tradition. The earliest Egyptian military ships appear in records from the Old Kingdom, but it is in the New Kingdom period, beginning around 1550 BCE, that the Egyptian navy developed into a significant and well-documented force. The New Kingdom pharaohs pursued an aggressive imperial policy in the Levant and in Nubia, and both campaigns required naval support. River transport for the Nubian campaigns on the Upper Nile, and coastal operations and supply convoys for the Levantine campaigns. The Thutmoside pharaohs of the 18th dynasty, who built Egypt's territorial empire to its greatest extent, maintained a river fleet on the Nile of considerable size, and their successors, who faced the Sea Peoples, most notably Rameses III, built the coastal and estuarine battle fleet depicted in such vivid detail at Medinet Habu. The Medinet Habu reliefs show Egyptian warships of a type quite different from the merchant vessels and royal barges depicted in other New Kingdom contexts. These are higher-sided, with a more pronounced fighting deck running the length of the hull, and they are equipped with what appear to be defensive screens, barriers of woven material, or possibly of overlapping reed bundles, protecting the oarsmen from missile fire. The rigging is furled, suggesting that these are fighting under oar power alone rather than under sail, which is consistent with the tactical demands of a naval battle in the enclosed waters of a coastal lagoon or river mouth. The archers stationed on the fighting deck are depicted in the midst of combat, firing into the crowded Sea People ships that are shown in various states of disorder and distress. The tactical picture at Medinet Habu is consistent with what we know of ancient naval warfare in general. It was brutal, close-quarters work in which the primary weapons were arrows, thrown spears, and the physical contact of ship against ship. The ram that becomes so prominent in Phoenician and Greek warships of the first millennium BCE is not clearly visible in the Medinet Habu reliefs, which may reflect the different tactical approach of Egyptian naval warfare, or may simply be an artifact of the artistic conventions used in the reliefs. Egyptian naval tactics seem to have emphasized missile fire and boarding rather than the ramming tactics that would characterize classical Greek and Phoenician naval warfare, and the relatively high freeboard of the Egyptian warships depicted at Medinet Habu is consistent with a vessel designed to provide a stable platform for archers rather than a low, fast ram weapon. The logistics of maintaining a naval force presented challenges quite different from those of building a single ship for a specific expedition. A naval force requires not just ships, but a continuing supply of men, food, materials, and the maintenance capacity to keep vessels in serviceable condition. Ship maintenance in the ancient world was a constant requirement because wooden hulls immersed in seawater are subject to attack from multiple directions simultaneously. Marine boring organisms drill through the planking from outside, while wood-rotting fungi attack from inside, where condensation accumulates and ventilation is poor. Ancient shipwrights maintained their hulls by periodic hauling out to dry them, removing borers, replacing damaged planks, recorking seams, and treating the exterior with substances intended to deter future infestation. The treatment of ancient ship hulls against marine borers, primarily the shipworm Teredo navalis, a remarkable animal that is not actually a worm but a bivalve mollusk that bores through wood using a specialized drilling organ and can reduce a sound plank to a hollow tube in a single season, was one of the most practically important aspects of ancient ship maintenance. The shipworm problem was well understood in antiquity. Ancient sources mention ships being destroyed by worm damage, and the coating of hulls with various substances to prevent it was standard practice across all the ancient maritime traditions. Lead sheathing, which physically prevents the shipworm's drilling organ from reaching the wood, was used on Greek and Roman warships. Pine tar and tallow mixtures were used on merchant ships. Bitumen on Mesopotamian vessels. Various plant-based preparations in the Indian Ocean tradition. None of these was as effective as the modern copper sheathing or anti-fouling paint, but all of them provided significant protection and extended the life of the hull materially. The Nile fleet of ancient Egypt served not only military, but also economic and ceremonial functions. The Nile was the highway of Egypt, and every significant movement of people, goods, or materials relied on it. The annual flood that made Egyptian agriculture possible deposited its silt across a wide floodplain, and the transport of grain from the agricultural provinces to the royal storehouses, of stone from the quarries of the south to the building sites of the north, of the administrative apparatus of the state from place to place as the pharaoh moved his court. All of this was river transport, conducted by a fleet of specialized vessels, ranging from small passenger boats to enormous cargo barges capable of carrying obelisks weighing hundreds of tons. The obelisk-carrying ships deserve particular attention as evidence of what ancient Egyptian shipbuilders could achieve when the demand required it. The largest Egyptian obelisks weigh several hundred tons and stand more than 30 meters tall. Transporting one from the granite quarries at Aswan in the far south to the temples at Karnak and Luxor, several hundred kilometers downstream, or to the temples at Heliopolis near the delta, more than 1,000 kilometers away, required ships of extraordinary carrying capacity. Hatshepsut's obelisks, two of them, each weighing approximately 300 tons, were transported from Aswan to Karnak on a ship that ancient accounts describe as approximately 60 meters long, the largest Egyptian vessel whose dimensions are recorded. No such ship survives, and the accounts may be somewhat exaggerated, but the basic engineering challenge is real. And the fact that multiple obelisks were successfully transported over such distances means that the ships used to carry them were genuine achievements of naval architecture, built without metal fasteners on the same mortise and tenon, lash and rope principles as the smaller vessels we have direct evidence for. The site of Mersa Gawasis, known variously as Wadi Gawasis or Mersa Gawasis in the scholarly literature, sits in a narrow valley cutting through the coastal mountains of Egypt's eastern desert to the shore of the Red Sea, approximately 23 kilometers south of the modern industrial city of Safaga. From the coast road, it looks like most of the eastern desert, a landscape of brown and tan rock, minimally vegetated, baked by the sun. There is nothing immediately visible to suggest that this ordinary stretch of desert coast was, 4,000 years ago, the most important Red Sea maritime installation in the world, the staging point for expeditions to the exotic land of Punt and to the turquoise mines of the Sinai Peninsula. The site was first identified by a German archaeologist, Ernst Küster, in the 1970s, who noted the presence of ancient pottery and other artifacts on the surface. Systematic excavation began in 2001 under the direction of Catherine Bard of Boston University and Rodolfo Fatovic of the Università degli Studi di Napoli, and the results of their work over the following decade have transformed our understanding of ancient Red Sea seafaring. What they found was not a dramatic ruin of walls and buildings. The desert had destroyed or buried most of the surface structures, but a remarkable series of rock-cut caves that had been used as storage chambers for ship equipment, sealed with stone slabs, and then forgotten for nearly 4,000 years. The caves at Mersa Gawasis were dug into the soft coral rag limestone of the cliff face bordering the ancient harbour basin, which has since been cut off from the sea by the accumulation of beach sediment. They were excavated to create rectangular chambers, roughly 3 to 4 meters wide, 2 to 3 meters high, and 3 to 6 meters deep, large enough to store the disassembled components of a ship's hull in organized bundles. The cave entrances were sealed with large stone slabs, and the gaps were filled with rubble and sand, creating a storage condition so well sealed and so dry that the organic materials inside were preserved to a degree almost without parallel in ancient Egyptian archaeology outside the Valley of the Kings. The most spectacular single find from the caves was a coil of rope. Not the stub of a rope or a fragment, but a complete coil approximately 60 centimeters in diameter, still perfectly formed after nearly 4,000 years. Its original 3-strand twist still tight, and its esparto grass fibers still flexible enough to bend without breaking. Alongside it were more ropes, dozens of them, in varying degrees of preservation, some still coiled, some partially unraveled. And then, as the excavation proceeded, the planks, cedar planks, cut to precise rectangular cross-sections, their edges still showing the mortise cuts and the V-channels for lashing ropes. Oars, their blades carefully shaped, and their looms turned to oval, cross-section for comfortable gripping. Steering oars, wooden tools, pieces of the wooden fenders used to protect the hull sides when mooring against a stone quay. The inscriptions found near the caves were what placed these objects in their historical context. Several large limestone stelae, commemorative slabs carved with hieroglyphic texts by expedition leaders recording their voyages, were found in the area, along with smaller inscribed fragments. The texts named the expeditions they commemorated, the pharaohs under whose authority they were conducted, the gods whose protection was invoked, and in some cases the numbers of men who participated, and the goods that were brought back. The earliest of these inscriptions dated to the Middle Kingdom, the reign of Amenemhat III in the 20th century BCE. The latest dated to the early New Kingdom, the reign of Amenhotep II in the mid-15th century BCE. Together they bracketed a period of approximately 500 years, during which the Mersa Gawasis installation was in active use. The pattern of use suggested by the archaeological evidence is one of episodic but repeated activity. Expeditions would arrive at Mersa Gawasis, having crossed the eastern desert from the Nile Valley. A journey of several days on foot and by donkey, carrying ship components that had been stored since the previous expedition, or had been newly prepared in the workshops of the Nile Valley. At the Red Sea coast, they would reassemble the ships from the stored components, provision them, and set sail for Punt. Months later, they would return, unload the goods brought from Punt, disassemble the ships again, and store the components in the caves for future use. The organized storage of the ship components, their careful preservation against the desert conditions, and the regular maintenance implied by the variety of tool types found in the caves, all suggest a well-managed logistical operation with institutional continuity extending across centuries. This continuity is itself remarkable. Organizations that maintain complex technical operations across multiple generations, the skills, the knowledge, the materials, the relationships, are relatively rare in history, and their maintenance typically requires either very strong institutional support or very high commercial incentive. The Punt expeditions appear to have been supported by the institution of the Egyptian state itself, organized and funded by the royal court, staffed by officials and specialists appointed by the crown, and conducted with the authority and resources of the pharaonic government behind them. The inscriptions record the participation of high-ranking officials, treasurers, overseers, commanders of expeditionary forces, and the offerings made to the gods at the site suggest that the expeditions had a quasi-religious significance beyond their purely commercial value. The goods that made the Punt expeditions worth the enormous investment of organization, logistics, and risk were primarily incense, frankincense, and myrrh, but also included the living trees recorded by Hatshepsut's reliefs, electrum, a gold-silver alloy, ebony, ivory, and live animals. The total value of a successful Punt expedition was clearly substantial, but so was the cost: feeding, equipping, and paying the hundreds of men involved in an expedition lasting several months, procuring and maintaining the ships, organizing the desert crossing, and managing the trading relationship with the rulers of Punt. All of this required a sophisticated administrative and logistical apparatus of considerable scale. The Mersa Gawasis caves are a time capsule of this apparatus, sealed by the departure of the last expedition that used them, and never reopened until the 21st century. The people who stored those ropes and planks and oars in the dark cave chambers were fully confident they would return for them. Some circumstance, the end of the expedition program under a new pharaoh, a political crisis, the simple passage of time and change of priorities, prevented them from doing so. And so the equipment sat, perfectly preserved in the dry desert cave, until Bard and Fatovich's team rolled away. The stone slab and the fresh air of the 21st century entered the chamber for the first time in nearly 4,000 years. The significance of Mersa Gawasis extends beyond the specific finds to the picture it gives us of the entire ancient maritime enterprise. These were not casual voyages made by adventurous individuals with a few tools and a boat. They were organized national projects, backed by the full resources of a sophisticated state, using specialized equipment that was carefully maintained and stored between expeditions, conducted by trained specialists who had spent years learning the knowledge required, and sustained across centuries by the institutional memory of an organization that understood what it was doing and why it mattered. The Punt expeditions were, in the most precise modern sense, a national maritime program, and the 40-meter ships they built and sailed, without a single iron nail, were the program's primary capital asset. Any large technical enterprise is ultimately constrained by the geography of resources, where the essential materials are, how they can be accessed, and what must be exchanged to acquire them. Ancient shipbuilding was no exception, and the geography of the materials required for large wooden ships, primarily timber, but also rope fiber, caulking material, and the metal tools needed to work the wood, shaped the patterns of ancient maritime trade in ways that are worth understanding in their own right. The premier shipbuilding timber of the ancient Mediterranean world was, as we have seen, the cedar of Lebanon, specifically Cedrus libani. But cedar was not the only suitable timber, and different regions and traditions made do with what was available locally, supplemented by imports where the available local species were inadequate. The Mediterranean coast of what is now Turkey and Greece produced both fir and pine of adequate quality for ship planking, and classical Greek ships were often built from these species when cedar was too expensive or unavailable. The island of Cyprus had extensive cypress forests in antiquity. The island's modern name is thought to derive from the Greek word for copper, another of its famous exports. But its ancient Phoenician name may have been related to the cypress, and Cypriot cypress was used for shipbuilding across the eastern Mediterranean. In the Indian Ocean tradition, the geography of teak was the defining constraint. Teak grows naturally only in Southeast Asia and the Indian subcontinent, in a relatively narrow band of monsoon forest, where the combination of seasonal drought and high rainfall creates the conditions the tree requires. The best Indian teak from the forests of the Western Ghats was the most prized, but Burmese teak from the forests of what is now Myanmar was also exported from the early historic period onward. The logistics of moving teak from the forests of Western India to the building yards of Arabia involved a trade chain of considerable complexity, with the timber being cut, roughly shaped, and loaded on coastal trading vessels at Indian ports, and transported westward under the winter monsoon to Oman and the Persian Gulf. The rope fiber requirement was almost as significant as the timber requirement for traditions that relied heavily on rope for structural fastening. Esparto grass, the source of Egyptian lashing ropes, grows in the arid and semi-arid regions of North Africa and the Iberian Peninsula. The Egyptian supply came primarily from North Africa and perhaps from Sinai. The coconut coir used in Indian Ocean sewn boat construction is a product of the coconut palm, which grows in coastal areas throughout the tropical Indian Ocean and was available locally to most of the tradition's practitioners. Hemp, used for rope in various ancient traditions, was cultivated across a wide area from Central Asia to the Mediterranean. And its cultivation history is intertwined with the history of ancient trade in ways that are still being investigated by archaeologists. Copper, the primary metal used for woodworking tools throughout the period we have been discussing, came primarily from Cyprus, hence the Greek word for copper, kalkos kupros, Cypriot bronze, and from the mines of Sinai and the eastern desert of Egypt. The copper of Oman was also significant for the Gulf trade, as we have noted. Each of these sources was at a different location relative to the major shipbuilding centers, and the logistics of getting copper from the mines to the workshops. Smelted into ingots, traded through intermediaries, finally worked into adze blades and drill tips in the carpenter's workshop, added a layer of complexity to the already complex supply chain of ancient shipbuilding. Tin, needed with copper to make the superior alloy bronze, was the rarest and most expensive metal in the Bronze Age world because its sources were few and often very distant from the consuming civilizations. The major sources of tin accessible to the ancient Mediterranean and Near East were in Afghanistan, ancient Bactria, in the British Isles, the famous tin of Cornwall, in Iberia, and possibly in Central Europe. The distances involved in moving tin from these sources to the bronze makers of Mesopotamia and Egypt were enormous. and the trade routes required multiple intermediaries. This means that the true cost of a bronze chisel, or ords in ancient Egypt, was much higher than the material cost alone. It included the full logistical cost of moving tin from the far end of a long trade chain, and this cost was ultimately passed on to the shipbuilder who needed metal tools for his work. The consequence of this resource geography is that large-scale, high-quality shipbuilding was, in the ancient world, a capital-intensive enterprise that could only be sustained by states or very wealthy merchant organizations. The ordinary small boat, the fisherman's dugout, or reed craft or small plank-built harbor vessel, could be built from local materials with locally available tools by a small number of craftsmen with ordinary skills. But a 40-meter ship, built from imported cedar, fastened with copper edge-cut mortise and tenon joints, lashed with precisely made esparto rope, and requiring the sustained labor of dozens of specialists over many months. This was a project that only significant institutional backing could support. This is why the great ancient ships were royal projects. The Punt expedition ships were built by the pharaoh's workshops, using timber imported by the pharaoh's trading fleets, worked by craftsmen in the pharaoh's employ, and stored in facilities maintained by the pharaoh's administrative apparatus. The Uluburun ship was carrying, among other things, cargo that appears to have been the property of a royal household. The raw materials of kingship, the bronze and glass and gold and ivory that sustained the display of power. Even the Khufu ship, buried to serve its owner in the afterlife, was the product of a massive state investment in materials and labor that only the most powerful institution in the ancient world could have sustained. This concentration of maritime capital in royal or institutional hands is not merely a historical curiosity. It has important implications for understanding how ancient trade networks were organized and how they were sustained. The great trading expeditions of the ancient world were not driven purely by market forces in the modern sense. They were also driven by political imperatives, by the need of rulers to demonstrate their power and their access to exotic goods, and by the institutional momentum of bureaucracies that had developed expertise and invested capital in specific trading relationships over generations. When those institutions collapsed, as the Bronze Age palace economies collapsed around 1200 BCE, the great organized expeditions ceased, and the trade networks that depended on them contracted or simplified, even though the underlying demand for exotic goods had not changed, and the sailing knowledge still existed in the communities of sailors who had serviced those expeditions. The recovery of those networks, when it came, was driven by different institutions. The merchant families and city-states of the Iron Age, who organized trade on a more decentralized and commercially motivated basis, using smaller ships and more flexible organizational structures that proved more resilient to the disruptions of political change. The Phoenician trading cities, the Greek merchant communities, the Arab trading families of the Gulf, all operated on this more commercially oriented model, and all produced the next generation of large wooden ships that continued the tradition of sailing long distances without metal fasteners.